Welcome, curious travelers, to Quiet Universe. Here, we wander into the profound, the mysterious, and sometimes the downright mind-bending realms of our cosmos. Today, we're diving into one of the universe's most astonishing marvels, the story of galaxy formation. Imagine a universe that began as an almost unthinkably hot, dense point. There was nothing, no stars, no planets, no galaxies, not even space or time as we know it. And yet, here we are, looking up at a sky teeming with galaxies, each one a vast, intricate collection of stars, planets, and gas. Every galaxy out there is part of this cosmic puzzle, formed from nothing but chaos, gravity, and the strange whispers of dark matter and dark energy. But how did all this come to be? How did galaxies, the very homes for stars and planets, including ours, emerge from a silent, formless early universe? Well, buckle in, because we're about to take a journey from the beginning of time itself, where we'll follow the birth of the first stars, delve into the mysterious nature of dark matter, and witness how different galaxies took on their unique shapes and structures. In this video, we'll explore how the Big Bang set the cosmic stage, how those tiny fluctuations in the early universe grew into seeds of galaxies, and the role of dark matter in making it all possible. We'll go on to see how the earliest stars blazed a path through the darkness, fusing simple elements into the building blocks of everything around us. And we'll dive into how galaxies grow, collide, evolve, and interact in ways that are still bewildering scientists to this day. So, settle in and let Quiet Universe take you on a cosmic journey across eons, from the very birth of galaxies to the unanswered questions that continue to confound our understanding of the universe. This is the tale of the formation of galaxies, and it's going to be a fascinating ride. The formation of galaxies is a story that began in the earliest days of the universe, and it reveals the delicate balance of forces, energy, and matter that has shaped the cosmos. To understand galaxy formation, we start not at the level of stars or planets, but in the intense, chaotic soup of particles that existed shortly after the Big Bang, around 13.8 billion years ago. In the first moments following the Big Bang, the universe was unimaginably hot and dense. Matter existed in the form of a plasma of subatomic particles like quarks, gluons, and electrons. As the universe expanded and cooled, particles began to combine, forming protons and neutrons, which in turn formed simple atomic nuclei in a process called nucleosynthesis. Eventually, the universe cooled enough to allow electrons to bind with these nuclei, creating neutral atoms and resulting in the release of photons. This moment, known as recombination, occurred about 380,000 years after the Big Bang and left an imprint we can still observe today in the cosmic microwave background, CMB. With the universe now transparent to light, a new phase began. Matter was distributed relatively evenly, but not perfectly so. Tiny fluctuations in density, as seen in the CMB, represented areas of slightly higher or lower concentrations of matter. Over hundreds of millions of years, these slight variations in density became the seeds for galaxy formation. Under the influence of gravity, matter in these slightly denser regions began to pull in surrounding matter, gradually growing denser and more massive. This process formed what we call dark matter halos. Dark matter, an elusive and invisible form of matter that does not interact with light, played a central role in this process. Dark matter's gravity provided the initial structure and framework within which regular matter, baryonic matter, could coalesce. Without dark matter, the gravitational pull in these early density fluctuations would not have been strong enough to overcome the expansion of the universe. Dark matter's gravitational skeleton essentially allowed galaxies to form by providing the gravitational well that captured baryonic matter, setting the stage for star formation. As gravity continued to pull hydrogen and helium gas into these dark matter halos, the gas began to collapse under its own weight, heating up as it did so. In the densest regions, temperatures and pressures became high enough to ignite nuclear fusion, and the first stars were born. These early, massive stars were short-lived but very bright, and their violent deaths in supernova explosions enriched the surrounding gas with heavier elements, seeding the interstellar medium for future star generations. Over time, the process of gas accretion and star formation continued, and clusters of stars began to take on more structured, stable forms. Galaxies grew by merging with each other, a process that was particularly common in the early universe. Smaller protogalaxies were drawn together by gravity, colliding and merging into larger and more complex galaxies. This merging process also likely triggered intense periods of star formation, as colliding clouds of gas compressed and ignited star birth on a grand scale. The evidence of this early galactic merging is still visible in many of today's galaxies, as scientists find signs of past interactions in their warped shapes and streams of stars flung far from their centers. Over billions of years, galaxies have continued to evolve. Spiral galaxies, like our Milky Way, formed when rotating disks of gas and stars settled into their characteristic disk shapes, with bright, star-filled arms winding outward from a central bulge. Elliptical galaxies, on the other hand, are thought to be the remnants of even more violent and chaotic mergers, resulting in a more spherical, featureless distribution of stars. The environment around a galaxy also influences its growth and shape. In dense galaxy clusters, gravitational interactions can strip galaxies of their gas, preventing new star formation and leaving behind older, redder stars. In isolated regions, galaxies may retain their gas longer and continue forming new stars. Galaxies are immense, complex systems of stars, dust, dark matter, and gas bound together by gravity, stretching across tens of thousands of light years. They're a cosmic masterpiece, each one unique, with billions of stars that have formed, evolved, and died over vast timescales. For us, they provide not only the stage on which our own solar system plays out, but also clues to the universe's past, present, and future. Understanding galaxies is essential because, by studying their formation and evolution, we begin to unravel the larger narrative of the cosmos. Galaxies didn't appear fully formed but arose from the chaotic early universe, a time of high-density energy and violent interactions. Initially, tiny density fluctuations existed in the primordial plasma after the Big Bang, and as this cooled and expanded, gravity began to amplify these variations. Matter began to clump together, forming small clouds that collided, merged, and evolved into protogalaxies. Over billions of years, these protogalaxies continued to merge, attracting stars and gas through gravitational forces to grow into the galaxies we see today. Each galaxy's shape, size, and composition reflect its formation history and the interactions it's had with other galaxies. Some are grand spirals, with arms stretching gracefully out from a central bulge. Others are elliptical, more amorphous and lacking the neat structure of spirals. These variations are due to the different ways galaxies interact and evolve. Collisions between galaxies aren't uncommon, and while they can be violent events, stars within galaxies are spaced so far apart that they don't often collide directly. Instead, the gravitational dance distorts and reshapes galaxies, often sparking waves of star formation. There's something compelling about how galaxies embody such a wide spectrum of life cycles and relationships. Like communities, galaxies grow and change through interactions, each one reflecting the environmental conditions it's experienced. In studying their structure, we learn not just about their formation but also about the nature of dark matter, the invisible substance that makes up most of a galaxy's mass and influences its shape and rotation. And since galaxies are distributed across the universe in patterns, their locations and movements tell us about the forces shaping the cosmos at the largest scales. When we look up at the night sky and see the faint band of the Milky Way, we're looking at just one of countless galaxies. Observing these systems opens a window into the universe's grand design, revealing the stages through which stars and systems develop, evolve, and sometimes fade. Galaxies are more than a collection of stars. They are the fundamental units of structure in the universe. Through them, we piece together not only where we come from, but also where we may be headed. The Big Bang was a cosmic beginning, not an explosion in the usual sense, but rather an unimaginably rapid expansion from an initial state of extreme density and temperature. In that moment, around 13.8 billion years ago, all the matter, energy, and space that would eventually become our universe began expanding outward from a point of infinite density. Picture it less like an explosion and more like the entire fabric of space itself stretching and unfolding, carrying with it the seeds for everything that would come to exist. Every galaxy, star, and planet, including our own. In those first fractions of a second, the universe was a seething hot soup of elementary particles, a plasma of protons, neutrons, electrons, and photons moving at incomprehensible speeds, all too energetic to combine into atoms or structures. But as this expansion continued, the universe began to cool, eventually reaching a temperature where protons and neutrons could fuse to form the nuclei of hydrogen and helium, the simplest elements. These primordial elements would serve as the building blocks of future stars and galaxies. Over the next 380,000 years, the universe kept expanding and cooling until it reached a point where these nuclei could finally capture electrons, creating neutral atoms, a process called recombination. As this happened, photons could travel freely through space for the first time, filling the cosmos with the afterglow we now observe as the cosmic microwave background, CMB. But it wasn't just the presence of matter that would lead to galaxies. There needed to be a guiding hand to shape it. Dark matter, the mysterious substance that makes up most of the universe's mass, played a crucial role. Though it doesn't interact with light and is therefore invisible, dark matter's gravity began to influence the ordinary matter around it. Tiny variations in density, thought to have originated from quantum fluctuations in the very earliest moments, were stretched and amplified by expansion. These slight differences in density allowed clumps of dark matter to form, creating gravitational wells into which gas could fall. These hubs of dark matter acted as anchors for what would become galaxies. As gas began to accumulate within these dark matter halos, it started to cool and compress, forming dense regions where stars could ignite. The earliest stars were massive, burning brightly and dying young in powerful supernova explosions, seeding their surroundings with heavier elements. This enriched material would be crucial for future generations of stars and the formation of planets, including rocky ones like Earth. Over time, stars clustered together, bound by mutual gravity, forming the first proto-galaxies. These small structures merged, collided, and evolved, gradually becoming the vast galaxies we see today. Each stage of this process reveals something essential about the universe's character. The Big Bang created a universe that was initially homogeneous, but its expansion and cooling allowed the emergence of complex structures. Gravity amplified the tiniest fluctuations, dark matter created the scaffolding, and matter itself responded, ultimately leading to the emergence of galaxies. Through these processes, the Big Bang didn't just set the stage for galaxy formation. It created the conditions for a universe of astonishing variety and scale, allowing stars to burn, planets to form, and, eventually, life to emerge on at least one small world. The formation of galaxies was part of this natural evolution, linking the dawn of the universe to everything that followed, weaving a grand cosmic story out of a single, fiery origin. In the seconds after the Big Bang, the universe was an incredibly hot, dense plasma of fundamental particles with temperatures reaching trillions of degrees. At this early stage, it was a chaotic sea of quarks, electrons, and photons, all packed together at unimaginable densities. Particles were smashing into each other with such intensity that they couldn't combine or form any stable structures. Time itself was only just beginning to take on meaning, as the rapid expansion of space started to stretch this ultra-dense, energetic state outward. Gravity, electromagnetism, and the nuclear forces were taking shape, and their interactions would soon start to shape the fundamental nature of matter. Within a fraction of a second, this chaotic plasma began to cool just enough to allow quarks to bind together into protons and neutrons, forming the first glimpses of atomic nuclei. But even then, temperatures were so intense that these particles couldn't yet form full atoms. This brief moment of particle formation, called baryogenesis, laid the foundation for matter in the universe, with a tiny imbalance between matter and antimatter allowing particles to survive rather than annihilate entirely. Within the first 3 minutes, as the universe expanded further, nuclear fusion kicked in, allowing these protons and neutrons to begin forming simple atomic nuclei. Hydrogen and helium emerged as the primary elements, with trace amounts of lithium, as these were the only elements that could form under such extreme conditions before the cooling became too rapid to support fusion. For the next few 100,000 years, the universe continued to expand and cool, but it remained an opaque fog. Free electrons roamed alongside photons, constantly scattering light and preventing it from traveling any significant distance. During this period, the universe was still so hot that atoms couldn't form because any attempt at bonding would immediately be broken by the intense energy around. This phase, called the photon-baryon plasma, was a cosmic soup where light and matter were entwined, with no real structures forming yet, just a homogeneous sea gradually spreading and losing heat. Around 380,000 years after the Big Bang, temperatures finally dropped to a point where electrons could combine with protons to form stable hydrogen and helium atoms, a process known as recombination. With electrons now bound into atoms, photons could move freely, and the universe transitioned from an opaque to a transparent state. This release of photons filled the cosmos with a faint afterglow that we can still observe today as the cosmic microwave background, CMB, a kind of fossil light that shows us what the universe looked like in its infancy. This transition was transformative. Light could finally travel across vast distances, and matter was now free to start organizing under gravity without constant interference from high-energy photons. For the next few 100 million years, the universe existed in a dark age, a period when it was transparent but void of any luminous sources. Gravity began pulling hydrogen and helium gas into denser regions, where tiny fluctuations from the early universe's quantum variations created a pattern of slight density differences. Over time, these clumps of matter grew, eventually forming stars and galaxies that illuminated the cosmos. These first stars, often much more massive and short-lived than our Sun, burned brightly and died in supernova explosions, releasing heavier elements that would enable future generations of stars and planets to form. So, in those first few moments, minutes, and thousands of years, the universe set itself on a path from pure energy to structure and complexity. Each phase was essential in creating conditions for the formation of galaxies and, ultimately, the diverse cosmos we observe today. Those early processes were the quiet architects, shaping a universe that would one day contain stars, galaxies, and everything else, laying out a framework of expanding space and cooling matter. A story billions of years in the making. The early universe is like a window into the mystery of existence, a place where everything that we see now, from vast galaxies to tiny particles, had its beginning. Right after the Big Bang, the universe was unimaginably hot and dense, filled with an opaque soup of particles and energy. In those first moments, particles collided constantly, creating and annihilating each other in a state so chaotic that not even light could travel freely. But as time passed and the universe began expanding and cooling, things started to change. After roughly 380,000 years, temperatures dropped enough for electrons and protons to combine, forming hydrogen atoms. This cooling phase marked a turning point, and light was finally able to escape from the dense fog and travel through space. This first light left a faint glow that still exists all around us, known as the cosmic microwave background, CMB. The CMB is a sort of photograph of the infant universe, a relic of the moment when light first broke free. The CMB isn't just some far-off glow. It's a map of the early universe. Looking at it, scientists can see subtle differences in temperature across the sky, small patches where matter was just slightly denser than the surrounding areas. These tiny fluctuations were the seeds of galaxies, stars, and planets. Over billions of years, those slight density variations attracted more matter, creating gravitational wells where particles gathered and began to clump together. This gradual accumulation of material eventually gave rise to galaxies and all the cosmic structures we see today. But there's a mystery that scientists are still working to solve. Observations show that there must be more to the universe than just visible matter. The stars, planets, and galaxies. There seems to be a hidden force, an invisible form of matter that doesn't emit or absorb light, but exerts a powerful gravitational influence. This is dark matter, and its fingerprints are everywhere, even though it can't be seen directly. When scientists map the CMB, they can trace how gravity from both visible and dark matter influenced the early stages of the universe. Dark matter helped amplify those small fluctuations in the CMB, creating the gravitational scaffolding that enabled galaxies to form. Without dark matter, those tiny variations might not have grown enough to create the structures we see today, and the universe as we know it would look drastically different. Thinking about the CMB and dark matter together is like exploring the echoes of ancient cosmic events that set the stage for everything we know. They represent a time and substance that shaped the world in ways we can hardly imagine, helping us understand not only the universe's structure but also a shared, ancient story embedded in the fabric of space and time. In the early universe, when everything was still chaotic and intense, small fluctuations in density were scattered throughout the primordial plasma. Imagine a universe filled with particles bouncing around, colliding endlessly, yet here and there, Some regions were just a bit denser than others. These tiny pockets of higher density were the result of quantum fluctuations that occurred in the very first moments of the universe's existence, a subtle but crucial variation that made some areas more crowded than others. These fluctuations might seem insignificant on the scale of the universe, yet they held an extraordinary potential. They became the foundations of galaxies, stars, and planets. All that exists now. These small, dense spots were like ripples in a vast ocean, but they weren't still. They were dynamic, constantly pulling matter toward them with the force of gravity. Because these regions had more mass, they had stronger gravitational pulls, and over time, they attracted more and more matter. This process was slow, almost imperceptible at first, but the gravity of these denser regions continued to draw in surrounding gas and particles. As more material accumulated, the gravitational pull became even stronger, forming the seeds of future galaxies. However, dark matter also played an essential role in this process. Though it doesn't interact with regular matter in any way we can see, it has mass, and therefore it has a gravitational influence. Dark matter's gravity helped stabilize these pockets of higher density by gathering around them, forming invisible scaffolding that held these regions together. Without this silent but powerful influence, the tiny density fluctuations would likely have dissipated, and the formation of galaxies might never have happened. These early seeds slowly grew, transforming over billions of years. Matter continued to fall inward, and the regions became dense enough to ignite stars. Stars gathered into clusters, and those clusters eventually formed galaxies. What started as an almost imperceptible difference in density evolved into complex cosmic structures. Today, when we look up at the stars or into a telescope, we're seeing the vast result of those initial tiny differences expanded and shaped by gravity into a universe filled with galaxies, star systems, and all the structures that make up the cosmos. The journey from those initial fluctuations to the stars and galaxies we see today is a tale of attraction, patience, and the invisible forces that brought the universe into its current form. In the early stages of the universe, when particles were cooling and light was finally able to travel freely, there was a quiet but profound force at work: dark matter. Although it doesn't emit light or interact with regular matter in the usual ways, dark matter has mass, and therefore it has gravity. A powerful force that helped shape the universe on a grand scale. Imagine the universe as a kind of cosmic web, where clusters and filaments of dark matter formed the underlying framework. Without dark matter, the early universe would have been like trying to build a house without a foundation. There would be matter, yes, but no real structure, no force to draw it together into galaxies, stars, and the cosmic architecture we see today. As the universe expanded and cooled, those tiny density fluctuations, regions where matter was ever so slightly denser, began to pull in more material. Dark matter, being more abundant than ordinary matter, gathered around these regions, amplifying their gravity. The invisible web of dark matter attracted clouds of gas and particles toward these denser spots, providing the gravitational support needed to help matter stick together. This wasn't a quick process. It took billions of years. But dark matter's influence was constant, encouraging these tiny regions to grow, forming the seeds of galaxies. Without dark matter's stabilizing presence, the gas and dust in the early universe would have scattered instead of clumping together. Its invisible mass provided the extra pull to prevent these forming structures from simply drifting apart. Dark matter created the gravitational wells deep enough for galaxies to form and hold themselves together. It acted as the unseen architect of the universe, gathering and binding material into the galaxies that, over time, would develop into diverse structures, from massive galaxies with superclusters of stars to small galaxies tucked into cosmic corners. When we look out into space, we're not just seeing the glow of stars and galaxies. We're seeing the enduring result of dark matter's work. It's a reminder of an unseen but essential force that, despite its invisibility, is woven into the history of everything we see. Dark matter helped create a universe rich with stars, planets, and galaxies. A structure that would not exist without its guiding hand. As the universe expanded from its initial dense state, dark matter began to clump together in a way that ordinary matter couldn't. Unlike regular matter, which interacts through forces like electromagnetism and is affected by radiation, dark matter is invisible to these forces. It doesn't collide or scatter in the same way. Instead, it feels only the pull of gravity, which allowed it to start forming dense concentrations earlier and more easily. Over time, these concentrations grew, forming what we now call dark matter halos. These halos are vast, spherical clouds of dark matter, invisible but incredibly influential. They were among the first structures to emerge in the universe, forming the backbone of everything that would follow. These halos had a profound role in shaping the cosmic landscape. They acted as gravitational anchors, pulling in ordinary matter that was free to move and interact in ways dark matter couldn't. Hydrogen and helium gas, the raw ingredients for stars, began to gather within these dark matter halos, drawn by the intense gravitational pull. Once inside, the gas started to cool and condense, eventually forming clouds dense enough to ignite into stars. The dark matter halos didn't just pull matter in, they held it, keeping the forming structures from dissipating and allowing galaxies to emerge and evolve. Dark matter halos continued to grow as they attracted more and more matter, merging and clustering into the large-scale structures that underlie today's universe. They became the silent framework around which galaxies, star clusters, and even superclusters formed. Without dark matter halos, the universe might have remained a thinly spread cloud of gas and particles, too diffuse to form stars or galaxies. But because dark matter was there first, clumping together and building this invisible scaffolding, it provided a place for regular matter to gather, grow, and ignite. The galaxies we see today owe their existence to these halos, to an unseen architecture that quietly shaped the entire structure of the cosmos. Imagine the universe as a vast, silent expanse, dark and cold, but filled with the potential for light. After the Big Bang, the universe was just a chaotic sea of particles, mostly hydrogen and helium, drifting in a haze of darkness for hundreds of millions of years. Gradually, as the universe expanded, it began to cool. These scattered atoms, caught up in the forces of gravity, started to pull toward each other, clustering together in faint, nearly invisible clouds of gas. In this early, primordial era, gravity was the driving force in a kind of cosmic dance. Wherever there was even the slightest density fluctuation, a region where particles were just a bit closer together, gravity would step in and amplify it. Tiny clusters of hydrogen atoms drifted closer, tugged by their mutual pull. It was a slow process, something on the scale of tens of millions of years, as these gas clouds continued to collapse inward, gaining more and more mass and density in the process. Each particle that joined added to the gravitational pull, and with that, the cloud would contract even further. Temperature and pressure began to build in the core of these clouds, a kind of hidden spark deep within, as the hydrogen atoms came close enough to collide and fuse together. The heat generated from this process started to reach extraordinary levels, in the millions of degrees, until finally hydrogen nuclei fused together, releasing a brilliant burst of energy. This marked the birth of the first stars. These newly ignited stars filled the universe with the first starlight, scattering photons into the darkness and illuminating the ancient cosmos. With this new starlight, the universe itself began to take shape. In the heat and energy of these massive, short-lived first stars, heavier elements began to form. When these stars finally died, they exploded as supernovae, spreading those elements far and wide. That dust, those elements, would eventually form the material for later generations of stars and planets. Each early star, in its brief, brilliant life, contributed to the universe's story, laying the groundwork for everything that would follow. Population 3 stars, those very first stars to ignite in the young universe, were the pioneers of all cosmic evolution that followed. They emerged when the universe was still in its infancy, a place of raw elements where only hydrogen and helium dominated, untouched by any of the heavier elements that we know today. Because of this elemental purity, Population 3 stars had unique traits, unlike any stars formed later. They were massive, often hundreds of times the mass of the Sun, and their sheer size meant that they lived fast and died young, burning intensely before exploding in violent supernovae. The birth of these Population 3 stars had consequences that shaped the universe in fundamental ways. As they burned, they produced light for the first time, breaking through the darkness and beginning the cosmic dawn. More importantly, in the intense heat of their cores, these stars created elements heavier than hydrogen and helium. Elements like carbon, oxygen, and nitrogen, essential for building planets, life, and future stars. When population 3 stars finally exhausted their fuel and exploded, they scattered these newly forged elements across space, seeding the vast regions between them. This interstellar enrichment set the stage for the next generation of stars and eventually for galaxies to take shape. These massive stars were crucial not just for the elements they left behind, but for their impact on the environment around them. Their supernova explosions and intense radiation heated the surrounding gas, which influenced how the next waves of star formation happened. Over time, these bursts of light, energy, and heavy elements brought order to the chaotic early universe, creating the seeds of future galaxies. Without population 3 stars, the universe would be a vastly different place, lacking the chemical diversity that allows galaxies, planets, and even life to exist. The first stars, blazing brightly in an otherwise dark universe, were like cosmic catalysts, leaving a profound impact on their surroundings. When these stars ignited, their intense radiation didn't just shine outward. It interacted directly with the dense clouds of hydrogen gas that filled the universe. As the stars emitted high-energy ultraviolet light, this radiation began to split apart the hydrogen atoms in nearby gas, knocking loose their electrons. This process, known as reionization, was a monumental shift, transforming the universe from a dark, opaque space into one that was increasingly transparent to light. These first stars didn't just light up their own small regions. As they broke down the hydrogen atoms around them, creating patches of ionized gas, they carved out expanding bubbles of reionized space. Each star contributed to these bubbles, and as more stars were born and died, the bubbles began to merge, eventually permeating vast regions of the universe. This collective effect gradually transformed the cosmos, dispersing the dense gas that had filled the early universe and allowing light to travel freely across space. This transformation wasn't just a visual change. It also altered the dynamics of galaxy formation. As reionization spread, it affected how matter clumped together, and over time, it set the conditions for galaxies to grow and develop within this changed cosmic landscape. Without the first stars and the process of reionization, the universe might have remained a murky, lightless place, unable to give rise to the rich structures we see today. These first stars acted like a bridge between the early chaotic universe and the structured one that followed, laying the groundwork for galaxies, stars, and planets to form in ways that made space hospitable to light and, ultimately, to life. In the early universe, stars emerged as some of the first cosmic objects in a vast, cold expanse of mostly hydrogen and helium. These first stars, known as population 3 stars, were massive, short-lived, and explosive by nature. Lacking the heavier elements present in stars today, they existed in a realm of simplicity, with few atomic ingredients to work with. Yet, these stars would set the stage for nearly everything in the universe we know. As they burned, these stars converted hydrogen into helium, releasing energy that gave the cosmos its earliest light. Their cores reached pressures and temperatures extreme enough to initiate fusion processes, transforming helium into elements like carbon, nitrogen, and oxygen. For a while, they burned with an intense, relentless energy, making some of the universe's first heavy elements. But their lifespans were brief, a matter of millions of years compared to the billions of years that most stars live today. When these massive stars finally reached the end of their lives, they didn't just dim out. They erupted in supernova explosions, scattering all the elements they had formed in their cores out into the cosmos. This spread of material, carbon, oxygen, silicon, iron, and more, was like sowing seeds. These elements blended into clouds of gas and dust, enriching them, and creating the raw material for future stars and planets. With each generation of stars that followed, this process of fusion and explosion continued, with each star becoming a kind of elemental alchemist, crafting and then spreading increasingly complex elements. Over time, these enriched clouds of gas began to collapse under gravity, giving rise to the next generations of stars, each progressively richer in elements. The gas would fragment into stars, planets, and asteroids, and each time a star formed and died, the universe grew a little more complex, its materials a little more diverse. The heavier elements allowed the formation of rocky planets and, in turn, created the conditions necessary for molecules to form that would eventually support life. So, through this cosmic cycle of birth, fusion, and explosive death, the universe transformed from a place of simplicity into one of almost infinite complexity. Each atom in our bodies traces back to these ancient explosions. We are, quite literally, made of stardust. And as we look up at the night sky, the stars we see are part of this cosmic lineage, endlessly continuing the cycle that began billions of years ago. In the earliest epochs of the universe, matter was scattered across space as isolated pockets of gas and dust. Gravity, that unseen yet all-powerful force, slowly drew these clouds closer together, creating small, densely packed star clusters. These clusters were like cosmic neighborhoods, small but vital communities of stars that marked the beginnings of galaxies. Over vast stretches of time, as gravity continued its quiet work, these clusters drifted together, merging and combining their masses, eventually building the foundations of young galaxies. In the chaotic environment of the young universe, these proto-galaxies would sometimes collide. These galactic mergers were turbulent, reshaping entire collections of stars and altering the paths of their orbits. But these mergers also triggered new bursts of star formation, as gas and dust compressed in the violence of impact. These stars were brighter, younger, and added energy to their evolving homes, growing galaxies into sprawling, luminous structures. As galaxies grew, they began to develop more intricate structures. Spiral arms formed in some, creating beautiful, winding patterns of stars and gas that stretched outwards like cosmic pinwheels. In others, stars settled into more spherical or elliptical shapes, depending on how the galaxy had merged or interacted with other galaxies. And, in their centers, massive black holes were born and fed on surrounding gas, shaping the galaxies around them with their intense gravitational influence. These black holes became like gravitational anchors, stabilizing the core and adding a deep gravitational pull that would impact the entire galactic structure. Meanwhile, galactic clusters, collections of galaxies bound together by gravity, were taking shape across the universe. Over billions of years, these clusters would grow as galaxies moved toward one another and merged in epic cosmic dances. Galaxies absorbed each other, their stars sometimes surviving to join a larger galaxy, while others were torn apart in the immense gravitational forces of the collisions. Each galaxy grew differently, molded by unique histories and interactions with neighbors. Some became grand spirals, rich in new stars and gas, while others evolved into elliptical galaxies, older and less active, their star-forming days largely behind them. The universe became a diverse mosaic of galaxies, each one shaped by its origins, its mergers, and its own complex history. As galaxies emerged and began to grow in the universe, their individual journeys led them down different paths, shaping their forms into spirals, ellipticals, or irregular structures. The precise dynamics and events a galaxy experienced played a critical role in determining its structure, each type a product of cosmic conditions, interactions, and chance. Spiral galaxies are the grand, swirling disks we often picture when we think of galaxies. Their formation is thought to hinge on a relatively quiet, stable life without major interruptions from outside forces. Gravity pulls gas and dust into a rotating disk where stars form in well-ordered patterns. Over time, this rotation carves out graceful arms that curve outward from a dense, glowing core. These arms aren't static, they're active sites of star formation, lighting up with young, hot stars. But spiral galaxies can only maintain this structure if they avoid large-scale disturbances, such as massive collisions with other galaxies. In their relative calm, they hold onto their gas and dust, continually forming stars and replenishing the beauty of their spiral arms. Elliptical galaxies have a very different story. They often arise from violent pasts, forged in the mergers and collisions of smaller galaxies. When two galaxies collide, the organized orbits of their stars are disrupted, and instead of a disk, the stars are spread in all directions. What emerges is a more random, spheroidal structure, like a cosmic cloud of stars rather than an organized whirl. Ellipticals are generally older, with less gas and dust, and as a result, they have little new star formation. Their stars are typically older and cooler, giving them a softer, redder glow. With their star-making days largely behind them, they remain as stable, quiet spheres or ellipses, relics of a more chaotic time. Then there are irregular galaxies, the wanderers of the cosmos that defy neat categorization. These galaxies have often been shaped by extreme gravitational forces or disruptive events. They might have come too close to a larger galaxy, which twisted and warped their shapes, or they might have survived a partial collision that left them misshapen. Unlike spirals and ellipticals, irregular galaxies lack a defined structure. Their stars scattered without the order of a disk or sphere. Often rich in gas, they're still forming new stars, but without the structured beauty of spirals or the balanced, mature shape of ellipticals. These varied shapes remind us that the universe is far from a peaceful place. Galaxies constantly interact, merge, or drift past each other, each encounter leaving a mark, shaping them in unique and lasting ways. The form a galaxy takes is a kind of cosmic fingerprint, a record of the events and forces that shaped it, marking it as a unique piece of the larger, ever-evolving structure of the universe. Galaxy mergers are among the most dramatic events in the universe, and they play a transformative role in shaping galaxies. When two galaxies begin their gravitational dance, they're drawn closer and closer until they collide, their stars intermingling and their structures morphing in the process. Contrary to what we might expect, individual stars within merging galaxies rarely collide with each other because of the vast distances between them. Instead, it's the galaxy's larger structures and gases that interact, with intense gravitational forces pulling stars into new orbits and generating massive waves of compressed gas. These waves of gas compression can spark new bursts of star formation, creating hot, bright, young stars that light up the merging galaxies like cosmic fireworks. As the merging continues, any organized structure the galaxies may have had is often shattered. Spiral galaxies, for instance, might lose their graceful arms as they collide, transforming into more chaotic or elongated shapes. Over time, as the galaxies merge into a single, larger entity, they often form an elliptical structure, with stars randomly distributed in all directions. This transformation tends to make the resulting galaxy more spheroidal, lacking the clear organization of a spiral but still holding the sheer size and star density of both original galaxies. These mergers also grow galaxies in mass and size. Each collision adds to the overall population of stars and often introduces new, heavier elements into the mix. With so many stars now crammed into a tighter space, black holes at the centers of these galaxies can also grow, feeding on nearby gas and dust or even merging with each other, creating even more massive central black holes. This can have dramatic effects on the galaxy's evolution. The supermassive black hole at the center can emit powerful jets of energy and radiation that blow away gas and slow down star formation, essentially halting the galaxy's growth for a time. Not all mergers are equal, of course. Sometimes a large galaxy will absorb a much smaller one, incorporating its stars and gas without too much disruption. These events are like cosmic snacks, absorbed into the larger structure with only minor changes to its shape or size. But in the case of two similarly sized galaxies merging, the effects are profound. The resulting galaxy becomes a patchwork of both galaxies' histories, their stars and gas combined into a complex tapestry of stellar populations and varying chemical compositions. The outcome of these mergers is ultimately a galaxy that is larger, often more stable, but fundamentally different from either of its original forms. This growth, by merging, has created some of the largest galaxies in the universe today. Massive, older galaxies that are often elliptical in shape and rich in ancient stars. Galaxy mergers, in this sense, are nature's way of evolving cosmic structures, blending, reshaping, and creating galaxies that continue to tell the story of the universe's restless, ever-changing nature. Galaxies are vast collections of stars, gas, and dust bound by gravity, each taking on a unique shape over millions or billions of years, shaped by their mass, energy, and interactions. A spiral galaxy, like our own Milky Way, is one of the most visually striking and recognizable. These galaxies are characterized by their graceful, winding arms that spread outward from a central bulge. This central bulge is often filled with older stars and, typically, a supermassive black hole. The spiral arms themselves are lined with younger, hot, blue stars, where new star formation is actively taking place. This structure can look somewhat like a pinwheel, with arms that spiral outward, wrapping around the galaxy's core in a cosmic dance. The spiral shape of these galaxies forms because of rotational forces and density waves within them. As a spiral galaxy rotates, regions of higher density, called density waves, form within the disk. These density waves compress gas and dust as they move through the galaxy, triggering star formation. The arms themselves are not fixed structures but rather more like traffic jams in the galaxy's disk, As material passes through these regions, stars are born, shine brightly for millions of years, and eventually die, giving the galaxy its sparkling, ongoing life. Gravity also plays a significant role in maintaining this structure, creating a beautiful balance that prevents the arms from collapsing or dispersing. Some galaxies don't have this defined, organized structure. Elliptical galaxies, for example, lack the structured arms of spirals and instead are more like large, featureless ellipsoids of stars. They contain older, redder stars and little gas or dust, meaning new star formation is rare. These galaxies are often thought to be the result of mergers between galaxies that destroy the organized structure of spirals. Irregular galaxies, as the name suggests, have no defined shape and appear chaotic, with no real pattern or symmetry. This could be due to gravitational interactions or collisions with other galaxies, which warp and disrupt their forms. Lenticular galaxies are like a middle ground between elliptical and spiral galaxies. They have a disk shape but lack significant spiral structure, often due to a depletion of gas necessary to form new stars, leaving them with older stars and little activity. The various shapes of galaxies aren't just visual distinctions. Each shape represents a different story of formation, evolution, and interaction within the universe. Every type of galaxy shows us a different phase of cosmic life, offering a glimpse into the forces and history that shaped the universe as it exists today. Elliptical galaxies are like the elder statesmen of the cosmos, vast and often ancient, with an appearance that's markedly different from the elegant spirals we see in galaxies like our own Milky Way. While spiral galaxies flaunt structured arms and defined shapes, elliptical galaxies are smooth, oval, or rounded, resembling a glowing halo rather than a neatly organized structure. This shape isn't an accident. It's largely the result of how they were formed and how they've evolved. Most elliptical galaxies are thought to be the products of past galactic mergers, where two or more galaxies collided and combined. The chaotic and energetic process of merging scrambles any pre-existing structure and strips away much of the gas that might have formed new stars. This leaves the resulting galaxy with a homogeneous, featureless shape filled with older stars, whose faint, reddish glow gives elliptical galaxies their characteristic color. Elliptical galaxies tend to have very little gas and dust, essential ingredients for the birth of new stars, which is why they don't sparkle with young, blue stars like their spiral counterparts. Instead, they're dominated by an older, more stable population of stars, a quiet, mature community compared to the lively, star-forming regions in spiral galaxies. This makes them less visually dynamic, but there's an elegance in their simplicity and steadiness. The stars in elliptical galaxies move in more random orbits rather than the organized rotation seen in spiral galaxies, contributing to their softer, more rounded appearance. The size of elliptical galaxies varies immensely. They range from small, dwarf ellipticals that are barely larger than a globular star cluster to gigantic ones, some of the largest galaxies in the universe. Their formation story means that they often appear near dense clusters of galaxies, where gravitational interactions and mergers are more likely to occur, shaping these giants over billions of years. In their own way, elliptical galaxies tell a story of time, collisions, and the long-term evolution of the universe. They're reminders of a different era, often found at the centers of galaxy clusters, calmly watching over younger, more vibrant galaxies, like elders who've seen it all and simply persist in their stately, timeless forms. Irregular galaxies are the nonconformists of the universe, with shapes that defy the organized structure we see in spirals and the smooth ellipses of elliptical galaxies. When you look at an irregular galaxy, there's no symmetry, no distinct center, no spiral arms. Just a chaotic spread of stars, gas, and dust. They seem almost unfinished, as though still in the process of forming or settling into a recognizable structure. This apparent lack of order often comes down to the events and forces that have shaped them over time. Many irregular galaxies started with more defined shapes, but gravitational interactions with neighboring galaxies disrupted them. This disruption can be powerful enough to distort their structure, tugging and stretching them out of shape, or even completely tearing their original formation apart. One of the main causes of an irregular structure is a close encounter or collision with another galaxy. When galaxies pass near each other, their mutual gravitational forces pull on each other's stars, gas, and dust, creating tidal forces that warp and deform their shapes. This can strip away material, send stars flying off course, and stretch the galaxy into unusual forms. In some cases, galaxies might even merge, combining their stars and gas but creating a shape that doesn't easily fit into the neat categories of spiral or elliptical. This cosmic interaction is a bit like a rough and tumble childhood. Irregular galaxies are shaped by their environment in a way that's almost turbulent, leaving them with jagged, often asymmetrical forms. Irregular galaxies also tend to be rich in gas and dust, and they're often actively forming new stars. Without the well-ordered structure of spiral arms, star formation here is more scattered, creating patches of brilliant, young, blue stars across their expanse. These galaxies often appear in groups or clusters where interactions with other galaxies are more common, their chaotic appearance hinting at the active forces at work within crowded regions of the universe. Because of their abundant star-forming material, irregular galaxies can be quite bright in certain regions, displaying bursts of light against the background of older, dimmer stars. While they may not have the same elegance or defined structure of other types, irregular galaxies are beautiful in their own unpredictable way. Each one tells a unique story of the universe's more dynamic forces, a kind of cosmic rough and tumble that leaves a lasting mark. They are reminders that not everything in the universe follows a set pattern and that beauty can be found in the wild, unpredictable forms that emerge when galaxies interact and reshape themselves. Irregular galaxies are full of surprises, and studying them gives us insight into the influence of gravitational forces, galaxy evolution, and the complex processes that create the diversity of shapes and forms we see across the cosmos. The rotation of gas and stars within a galaxy is like the heartbeat that shapes and defines its structure, a fundamental process that influences everything from its overall shape to the creation of new stars. In spiral galaxies, for example, this rotation is especially pronounced, with stars, gas, and dust all moving in orbits around a central core. This organized, swirling motion produces the beautiful spiral arms that stretch out from the galaxy's center. As material rotates around the core, regions of higher density waves, form in certain areas, compressing gas and triggering the birth of new stars. These new, hot, young stars give the arms of the spiral their luminous glow, and this continuous rotation keeps the spiral structure alive, like an engine generating both beauty and life within the galaxy. In elliptical galaxies, the story is different. Here, the stars don't follow a uniform rotation around a central core. Instead, they move in more random orbits, crisscrossing in various directions, almost like a cloud of fireflies darting in all directions rather than a group moving in sync. This lack of organized rotation results in a rounder, more featureless shape, with little in the way of arms or distinct structures. Without the rotation to organize material into spirals or other shapes, the galaxy takes on a softer, elliptical form, where stars simply cluster into a roughly oval or spherical shape. The stars in elliptical galaxies are often older, with little new star formation since there's generally less gas and dust to be compressed and ignited. In irregular galaxies, rotation, if present, is far more chaotic. Rather than a structured pattern of stars and gas orbiting in smooth paths, irregular galaxies experience more erratic movement. Often shaped by gravitational interactions or even collisions, the stars and gas in irregular galaxies might move in all directions, with no organized pattern to bind them into a defined structure. This turbulent rotation, or lack of any coherent rotation, gives irregular galaxies their scattered, asymmetrical appearance. It also means that star formation here is more unpredictable, happening in clumps wherever there's enough gas and dust. Rotation doesn't just give galaxies their shapes. It also keeps them stable, balancing the forces that would otherwise cause them to collapse inward under their own gravity. In a way, the rotation of gas and stars is a delicate dance, a self-regulating process that gives galaxies their form, whether they're elegant spirals, steady ellipticals, or chaotic irregulars. Without this rotation, galaxies might look very different, lacking the structures we're so familiar with. This ongoing motion is a quiet, powerful force, holding galaxies together across the eons and shaping them into the incredible forms we see today, each with its own unique rhythm and story within the vast canvas of the universe. When galaxies collide, it's one of the universe's most dramatic and transformative events. Imagine two vast, intricate structures made up of billions of stars, dark matter, gas, and dust slowly converging over billions of years, drawn together by gravity. As they approach, these galaxies don't crash together in a traditional sense. The stars are so far apart within each galaxy that they rarely collide directly. Instead, the gravitational forces between the two galaxies pull and stretch them, warping their shapes. This process gradually intertwines their structures, setting off waves of movement and disturbance that shake things up on a grand scale. As the galaxies dance around each other in a kind of cosmic embrace, their vast clouds of gas and dust come into contact, creating turbulence that compresses some regions of gas enough to trigger star formation. New stars ignite in spectacular bursts, known as starburst events, transforming parts of the galaxies into brilliant patches of light and energy. This spurt in star creation can lead to the formation of huge clusters of young, hot, massive stars, which shine brightly for relatively short lifetimes. As these massive stars die, they explode as supernovae, injecting energy back into the surrounding gas and further shaping the dynamics of the merging galaxies. Over time, the individual identities of the galaxies blur as they gradually settle into a new, unified structure. Spiral arms may stretch out or disappear, while new shapes, sometimes smooth, sometimes clumpy, emerge. Some galaxy mergers result in elliptical galaxies, which lack the orderly arms and structure of spirals and are instead more amorphous and densely packed. The fate of the galaxy's supermassive black holes is another fascinating part of the merger. As they drift toward one another, drawn in by gravity, they can eventually collide, releasing an enormous amount of energy and gravitational waves that ripple through space itself. Even after the merger is largely complete, the newly formed galaxy may remain active and chaotic for millions of years, with leftover gas and dust still fueling some star formation. Eventually, the galaxy can settle into a more stable structure. A galaxy's environment profoundly shapes its journey through the cosmos. In a galaxy cluster, where thousands of galaxies gather within a relatively small region of space, each galaxy is part of a larger, dynamic system. This environment is intense, with galaxies experiencing close encounters, near misses, and even collisions that nudge, tug, and sometimes disrupt them. Being surrounded by so many cosmic neighbors constantly exerts gravitational pressures, which gradually influences the shape, structure, and overall behavior of each galaxy. For instance, as a galaxy moves through the dense, hot gas that fills a galaxy cluster, it can experience a process called ram pressure stripping. Imagine the galaxy plunging through this thick, invisible medium. The gas within the galaxy, essential for creating new stars, is gradually swept away by the pressure, much like wind stripping leaves from a tree. As a result, the galaxy's ability to form new stars diminishes, often leaving it in a quieter, more passive state where only older stars remain, and the galaxy slowly fades to a more subdued appearance. The constant gravitational interactions also reshape galaxies over time. Nearby massive galaxies, or even the collective gravity of the entire cluster, can pull and stretch a galaxy, distorting its form. Some spiral galaxies, under these conditions, lose their distinctive arms and eventually morph into elliptical shapes. This isn't just a passive change. It means the galaxy's internal structure, star formation, and life cycle are all fundamentally altered. In these cluster environments, galaxies often end up more spherical and lack the kind of active star-forming regions seen in galaxies that exist in more isolated settings. Some galaxies and clusters may find themselves slowly drifting toward the cluster center, where a massive, luminous galaxy often resides. As they fall inward, the gravitational forces intensify, and the interactions become more frequent and violent. Over time, smaller galaxies may be absorbed entirely, their stars and matter merging with the larger, central galaxy. The remnants of these smaller galaxies can often be detected as faint streams of stars orbiting the center, like trails of cosmic breadcrumbs that trace the galaxy's journey to its final resting place. In these dense environments, galaxies change in ways that they never would in isolation, with each one contributing to and being molded by the collective forces of the cluster. The cluster environment essentially accelerates their evolution, pushing them toward stability by depleting their star-forming materials, reshaping their structures, and sometimes leading them to merge into larger, more stable forms. This complex dance plays out over billions of years, with each galaxy subtly transformed by its environment, shaped by the crowd it moves with, and carrying the marks of countless gravitational interactions. Galaxy harassment is a fascinating and harsh process that plays out in crowded galaxy clusters, where countless galaxies move in close quarters. Picture a small galaxy navigating through a bustling cluster packed with massive neighbors. Every time it passes near one of these larger galaxies, it feels an intense gravitational pull that tugs at its stars, gas, and overall structure. This constant barrage of gravitational forces doesn't destroy the galaxy all at once, but instead takes a toll over millions, sometimes billions, of years. Bit by bit, each encounter disturbs and destabilizes it, like gentle but persistent waves battering a small boat on a stormy sea. As the smaller galaxy endures one close pass after another, its stars are thrown into new orbits, distorting the galaxy's shape and often transforming it from a neat spiral into a more chaotic, irregular form. The gas within it, essential for creating new stars, can be stripped away over time. Each encounter with a larger galaxy pulls some of this gas out, and without it, the smaller galaxy's capacity for star formation declines. What was once a vibrant, star-forming galaxy can become a faded, aging structure filled mostly with older stars that no longer have the youthful sparkle of new star formation. This process also causes some stars to be pulled out of the galaxy entirely, leaving trails of stars behind that eventually scatter into the cluster. These stars may end up drifting alone, no longer bound to any single galaxy, forming what's known as intracluster light, a faint, ghostly glow that fills the spaces between galaxies in the cluster. This scattered light is a reminder of the galaxy's slow dismantling and reshaping under the relentless pressures of the cluster environment. The cumulative effect of all these gravitational interactions leaves small galaxies and clusters more vulnerable and diminished compared to those in more isolated regions of space. Galaxy harassment slowly saps them of the material and energy they need to maintain their structure and vitality. Over time, they lose not just their original shape, but also their ability to evolve as they might have outside the cluster. They become quieter, simpler forms, often stripped of the brightness and complexity they once had. In this crowded cosmic setting, these small galaxies are constantly influenced and reshaped by forces beyond their control, their paths determined by the vast and powerful neighbors that surround them. Gas and dust within galaxies play a fundamental role in the birth of stars, unfolding a process that begins with seemingly ordinary clouds of material drifting through space. These clouds of gas, mostly hydrogen and helium, along with dust particles, are the raw ingredients. They're often cold and dark, quietly existing until they encounter something that stirs them to life. Perhaps a shockwave from a nearby supernova or the gentle pull of gravity from a neighboring region. This disturbance creates a ripple effect, causing the gas and dust to collapse inward. As this happens, the particles become denser, and the gravity within the cloud starts pulling everything even tighter together. The cloud's structure begins to change. Regions inside it become so dense that gravity takes over completely, drawing everything toward the heart of the forming star. In this collapsing core, the gas and dust particles press together with enough force that their temperatures rise dramatically. The cloud heats up, and soon, the growing pressure inside gives rise to a new level of energy. Hydrogen atoms in the core begin to collide with such speed and force that they start to fuse, forming helium atoms and releasing a tremendous amount of energy. This energy is what we see as starlight, and at this stage, the core finally lights up as a newborn star. The presence of dust is critical in this entire process, though it might seem like an unlikely ingredient in something so vast as star formation. Dust particles help cool down the gas by absorbing and re-radiating heat. This cooling allows the gas to continue contracting, an essential part of reaching the critical density for star formation. Dust also acts as a shield, protecting these fragile nurseries from the galaxy's background radiation, letting the collapse unfold undisturbed. Once the star has formed, it doesn't stop there. The newborn star sends out powerful stellar winds and radiation, pushing away the surrounding gas and dust. This can halt further star formation nearby, but it also disperses these materials to new regions of the galaxy. Sometimes, these winds push enough material together in another spot, sparking the formation of new stars. So, galaxies become places of repeated birth and renewal, with gas and dust cycling through this process, fueling new generations of stars. The stars, in turn, contribute heavier elements back into the galaxy when they die, enriching the gas and dust available for future star formation. linking each generation of stars to the next in an unending cosmic story. Star formation begins when dense regions within vast clouds of gas and dust in galaxies experience something powerful enough to disrupt their quiet state, triggering the gravitational collapse that will eventually form stars. This spark can happen in various ways, and the nature of these triggers varies between different galaxies. In spiral galaxies like our Milky Way, the process is often set off by the rotation of the galaxy itself. As spiral arms sweep through space, they create zones of denser gas, which sometimes compress the clouds just enough to start the collapse process. Within these dense arms, massive stars are born, shining brightly and shaping the regions around them. The presence of neighboring supernova explosions in these galaxies also has a profound effect. When a massive star reaches the end of its life and detonates in a supernova, the powerful shockwave created pushes nearby gas, sometimes compressing it enough to form new stars. Elliptical galaxies, however, present a different story. Typically containing older stars and less dense gas, ellipticals lack the active spiral arms and usually don't have as many supernova shocks to fuel continuous star formation. Here, star formation is far less frequent and often occurs under special circumstances, like when an elliptical galaxy collides with another galaxy. This type of merger can inject fresh gas and dust or restir existing clouds, briefly reigniting star formation. In contrast, irregular galaxies, which lack the structured arms of spirals and the calm of ellipticals, present a chaotic picture. With their irregular shapes and often turbulent internal environments, star formation in these galaxies tends to happen in bursts. Small-scale gravitational interactions within the gas can occasionally create pockets dense enough for stars to form, and the activity is often fast-paced and clustered. Irregular galaxies are also highly susceptible to nearby galactic influences. Interactions with passing galaxies or jets from supermassive black holes can introduce disturbances that prompt waves of new star formation. Thus, while every galaxy holds the same basic ingredients for star formation, the story differs from one to the next. Factors like galactic structure, the distribution of gas, and external influences play unique roles in triggering the collapse of gas and dust into new stars. Whether in a calm elliptical, a spiraled Milky Way-like galaxy, or a chaotic irregular galaxy, each galaxy has a story driven by the interplay between gravity, energy, and time. The diversity of conditions across galaxies makes star formation a truly cosmic phenomenon, rich in variation and endlessly renewed across the universe. The amount of gas in a galaxy is like a reservoir of potential, directly influencing how quickly and actively it can create new stars. Galaxies with large amounts of gas have more of this essential raw material for star formation, allowing for higher rates of activity. When a galaxy is rich in gas, especially the cold hydrogen gas needed for star-forming regions, it's primed for forming new stars. In regions where dense clouds of this gas exist, it only takes a disturbance, such as a passing star, a shockwave from a nearby supernova, or the influence of a spiral arm, to set the process in motion. The abundant gas can quickly fuel multiple star-forming regions at once, creating a dynamic galaxy with vibrant star nurseries and a high rate of new stars emerging over time. On the other hand, galaxies with limited gas struggle to sustain any significant star formation. Over time, as galaxies create stars, they gradually consume their gas reserves, and without new gas to replenish the supply, the star formation rate declines. Older galaxies, like many ellipticals, often contain very little gas compared to younger spiral or irregular galaxies, which are still flush with this material. With minimal gas available, star formation becomes a rare event in these galaxies, and they take on a quieter, more aged look as they lose their youthful, active glow. The availability of gas also shapes how galaxies evolve. In galaxies with high gas content, the continuous formation of stars leads to a cycle where young, hot stars create energy that can heat the surrounding gas, sometimes even pushing it out to the galaxy's edges. In extreme cases, like starburst galaxies, star formation proceeds at such an intense rate that the energy output drives much of the remaining gas away from the galaxy entirely. This gas ejection can slow future star formation, effectively setting a limit on how active a galaxy can be over time. Meanwhile, galaxies can also gain gas from their environment, which can fuel new rounds of star formation. Galaxies that interact with or collide into other galaxies often experience a surge of gas flowing inward, creating a renewed burst of star formation. These interactions show how the available gas doesn't just determine a galaxy's current rate of star formation, but also holds the key to its longer-term evolution. The amount of gas isn't just a number. It's a living factor that shapes a galaxy's story, dictating how stars are born, how they eventually fade, and how the galaxy itself transforms across cosmic time. When we think about galaxies, it's almost like trying to understand the nature of an entire world. Not just how it exists now, but how it came to be. Galaxy formation is essentially that quest to piece together the origins of these vast cosmic structures. Scientists have spent decades developing and refining theories that aim to explain how galaxies, from small dwarf galaxies to massive spirals like the Milky Way, have taken their forms over billions of years. While the details are complex, the foundational theories provide two distinct lenses through which to view the story of galaxy formation. One of the early approaches, known as the top-down model, proposes that massive regions of gas in the early universe cooled and collapsed to form large structures, which then fragmented into galaxies. In this model, the entire process is like an organized dance, with large clusters coming together first, and then smaller galaxies emerging from this initial cosmic choreography. But this view has evolved because, in reality, observations didn't fully align with this large-scale approach. Evidence has shown that many galaxies and clusters don't look quite like they're all pieces from one original massive body. Instead, they seem to have more independent origins. The alternative bottom-up or hierarchical model has gained more support in recent decades, largely because it aligns with the observed distribution of galaxies in the universe. In this model, small clumps of matter formed first and later merged to build up the more massive galaxies we see today. In essence, it's a cosmic assembly line, where small galaxies and proto-galaxies coalesce and merge over time, gradually growing into larger structures. It suggests a more chaotic and piecemeal process where galaxies collide, interact, and merge, creating spirals, ellipticals, and irregular galaxies as they reshape over billions of years. Observations of distant galaxies in their youthful, more chaotic forms provide support for this model, capturing snapshots of merging galaxies that eventually settle into more stable forms. More recently, advancements in computer simulations have helped scientists test these theories in detail. Using vast amounts of data, simulations can recreate the early universe, adding layers to these theories. These simulations have revealed the critical role of dark matter, an unseen but gravitationally influential component that seems to drive the formation of galaxies. Dark matter clumps together, creating gravitational wells that pull in ordinary matter, which then forms stars and galaxies within these structures. In both models, dark matter is essential, but the role it plays is often more clearly demonstrated in hierarchical simulations. Without dark matter, the galaxies we observe simply wouldn't have enough gravitational pull to bind together. Still, both models have their limitations and unanswered questions. For instance, how do galaxies maintain their stable shapes, such as spirals, for such long timescales? Or, how do supermassive black holes at galaxy centers influence their surroundings? In reality, galaxy formation likely involves a mix of these ideas. Smaller clumps merging in a bottom-up process, influenced by larger structures on the cosmic scale that resemble aspects of the top-down idea. It's an intricate, layered process where galaxies are born, evolve, and sometimes collide, leading to entirely new forms and characteristics. Studying galaxy formation is like reading the biography of the cosmos. Every insight into how these giants formed offers clues about the overall structure and evolution of the universe itself. The hierarchical model of galaxy formation imagines galaxies coming together through a series of small beginnings, where the process is less about grand designs and more about gradual assembly. Instead of galaxies forming all at once, they begin as small clumps of matter that, over immense periods of time, combine to create the larger structures we see today. Picture it as a cosmic patchwork, with the universe building galaxies in stages. These small clumps, known as halos, are gravitationally bound pockets of dark matter that pull in surrounding gas and dust. As this gas cools, it condenses into stars, forming the earliest protogalaxies. Over time, these small protogalaxies merge and cluster together, creating larger and larger galaxies through a process of accumulation. In the early universe, everything was more chaotic and dense, with frequent collisions and interactions between protogalaxies. These interactions were sometimes violent, leading to intense bursts of star formation and sometimes they caused galaxies to reshape dramatically. This constant merging and remerging of smaller galaxies built up the more massive galaxies we see today, with each merger bringing its own characteristics and sometimes creating new structures, such as spiral arms or elongated halos. Dark matter plays a quiet yet critical role in this model. It's thought to exist as an invisible framework around which galaxies form. Because dark matter has a gravitational pull but doesn't emit light, it creates a kind of cosmic scaffolding. Regular matter falls into these dark matter halos, beginning the formation of stars and, eventually, galaxies. Without the gravitational influence of dark matter, the small clumps of gas and dust might never come together with enough force to form stars, let alone galaxies. Dark matter essentially sets the stage, providing the gravitational foundation for galaxy formation and driving the merging process. One remarkable aspect of the hierarchical model is how it explains the large-scale structure of the universe as a cosmic web. The earliest small proto-galaxies formed along these dark matter filaments, like beads on a string. As they merged, larger galaxies and galaxy clusters formed at the intersections of these filaments, creating the universe's vast and intricate structure. This model accounts for the way galaxies are distributed across space today, not randomly scattered but clustered in webs and chains, connected by this underlying framework of dark matter. The hierarchical model also suggests that the variety of galaxies we see, spiral, elliptical, irregular, resulted from the different ways galaxies have merged over time. For instance, when two large galaxies collide, they may form an elliptical galaxy, which is more chaotic and less structured than a spiral. Spirals, on the other hand, may have evolved through less disruptive mergers or interactions, allowing them to maintain their arms and rotational symmetry. The hierarchical model is still evolving as new data and simulations refine our understanding, but its core idea, that galaxies grow through accumulation, starting small and merging over time, has transformed how we think about galaxy formation. It paints a picture of a universe that creates beauty through a series of chance interactions and steady accretions, where galaxies emerge as the universe weaves together its stars, gas, and dark matter into the dynamic structures we observe today. When scientists want to understand galaxy formation, they're dealing with events that span billions of years and distances that boggle the mind, so direct observation alone isn't enough. This is where computer simulations become essential. These simulations allow researchers to recreate the physical conditions of the early universe and watch galaxies form and evolve in a virtual space. With the power of supercomputers, scientists input the basic laws of physics and elements like gravity, thermodynamics, and the properties of dark matter and dark energy, letting these simulations run through the complex, chaotic interactions that shape galaxies. In a way, simulations provide a controlled environment, a digital laboratory, where scientists can run and rerun scenarios to test how galaxies might behave under different conditions. For instance, they can simulate the effects of gas cooling rates, star formation rates, and the influence of supermassive black holes on surrounding matter. They also account for dark matter, whose gravitational pull is crucial in pulling gas and dust together, creating the framework for galaxies to form. Through simulations, scientists get to watch this process unfold, seeing how small structures come together to create larger ones over billions of years, mimicking the stages of galaxy growth in a fraction of the time. These virtual universes aren't just guesswork. They're constantly checked against actual observations from telescopes and space probes. For example, if a simulation of galaxy collisions predicts a certain shape or distribution of stars, scientists can compare it with the patterns they see in real galaxies. When simulations match observations, it suggests the model is accurate. When they don't, scientists can tweak parameters, perhaps adding the influence of dark energy or adjusting how gas cooling might vary with galaxy size. These adjustments are crucial because they often reveal previously unknown dynamics of galaxy formation, helping refine our models. One of the powerful insights from simulations is how chaotic the early universe was and how often galaxies collide and merge. Observationally, scientists have seen snapshots of merging galaxies, but in simulations, they can watch the entire event in slow motion, tracing how each collision reshapes the galaxies involved. They can even test what happens when galaxies of different sizes collide or when a galaxy passes close to a massive cluster, revealing interactions that create a range of structures, from spirals to ellipticals to irregular galaxies. Another fascinating aspect is that simulations can capture the role of supermassive black holes in galaxy centers, revealing how these cosmic giants can affect the surrounding gas, sometimes triggering intense bursts of star formation and other times stifling it. This interaction, known as feedback, shows how black holes may help regulate a galaxy's growth, adding a layer of complexity that's challenging to study observationally but comes to life in simulations. In the end, simulations are the closest thing scientists have to a cosmic time machine, allowing them to piece together the life cycle of galaxies. As computing power grows and more data from the universe becomes available, these simulations become more accurate, more detailed, and offer deeper insights, helping us to better understand the vast and intricate process of galaxy formation. Understanding how galaxies form and evolve is one of the most profound quests in astronomy, and observing distant, early galaxies gives us clues about how the universe itself was born and grew up. Because light takes time to travel, we see these ancient galaxies not as they are now, but as they looked billions of years ago, when they were still young. To observe them, astronomers use some of the most powerful telescopes on Earth and in space, like the James Webb Space Telescope and the Hubble Space Telescope. These observatories are like time machines, collecting faint light that has journeyed across the cosmos, giving us a glimpse into the universe's past. Astronomers rely on a few key techniques to capture this light and piece together the story of galaxy formation. They first look at the color and shape of galaxies. The most distant galaxies are usually reddish, as their light is redshifted due to the expansion of the universe. This shift stretches the wavelengths of light, so by analyzing how red a galaxy appears, astronomers can calculate how far away it is and, by extension, how old it is. Galaxies that formed just a few 100 million years after the Big Bang appear as dim smudges, lacking the well-defined spirals or ellipticals we see in more mature galaxies. They're often chaotic and irregular, which reveals clues about their early formation stages, where gravity and turbulence were sculpting them into recognizable shapes. One of the biggest challenges in observing these early galaxies is that they're incredibly faint. These young galaxies emit primarily in the infrared range because they're redshifted so much. Ground-based telescopes struggle to capture this faint infrared light, so astronomers use space-based telescopes that can observe without the interference of Earth's atmosphere. By capturing infrared images, they can see through cosmic dust that often shrouds these galaxies, revealing the faint details of stars and structure within. This ability to observe in infrared was one of the key advances with the James Webb Space Telescope, which has already pushed our observational limits further back in time. Spectroscopy also plays a crucial role. When astronomers study the light from galaxies, they break it down into spectra, which reveals the chemical fingerprints of the elements within. These spectral lines tell us what kinds of elements were present in the early universe and how quickly stars were forming. The first galaxies likely had little to no heavy elements like those we see in stars today. Instead, they were mostly composed of hydrogen and helium, forged in the aftermath of the Big Bang. As the galaxies evolved, massive stars within them would fuse these elements into heavier ones, releasing energy that drove new rounds of star formation. Spectroscopic data from distant galaxies allow astronomers to track this process over billions of years. Another challenge is the sheer number of galaxies and their rapid changes. Galaxy formation isn't a neat, orderly process. It's messy, full of collisions and mergers, where smaller galaxies combine to form larger structures. By observing clusters of galaxies at different distances, astronomers get snapshots of various stages in this chaotic evolution. Galaxy clusters and superclusters reveal how galaxies interact gravitationally and how dark matter may be influencing their structure. These interactions shape galaxies' eventual shapes, turning some into the majestic spirals and others into elliptical giants. Each observation is like adding a puzzle piece to a larger picture of cosmic history. By piecing together the different ages, types, and structures of galaxies, astronomers can work out how they grow, evolve, and, ultimately, how they relate to our own Milky Way. It's a slow process, requiring years of detailed observation and analysis, but each new discovery adds to a narrative that began nearly 14 billion years ago, giving us insights not just into these ancient galaxies, but into our own place in the cosmos. The Hubble Space Telescope, launched in 1990, has been essential in reshaping our understanding of galaxy formation and evolution, giving astronomers an unfiltered view into deep space that's simply not possible from Earth. Before Hubble, our knowledge of galaxies at large distances, especially in their early stages, was limited by the distortion of Earth's atmosphere. With Hubble in orbit, above the turbulence of the atmosphere, astronomers gained a clear and direct line of sight into the cosmos, allowing them to see galaxies as they were billions of years ago, right after the Big Bang. One of Hubble's most revolutionary contributions has been its deep field images, where it stared at seemingly empty patches of sky for days on end. These images revealed thousands of galaxies, many of them extremely faint and distant, hidden beyond the reach of previous telescopes. By pushing the limits of its sensitivity, Hubble has shown us a chaotic but fascinating mix of tiny, irregular galaxies, many in the process of merging or colliding. These galaxies appear as they did more than 13 billion years ago, when the universe was young and galaxy formation was still in its infancy. This view allows astronomers to see galaxies not as they are now, in their evolved states, but in their raw, early forms, providing snapshots of how galaxies begin to take shape. Hubble's sharp, high-resolution images let astronomers study the structure and composition of galaxies in incredible detail. Unlike earlier observations that only offered blurry, distant smudges, Hubble shows spiral arms, bar structures, and the star clusters within them. With its onboard instruments, it can detect light across a wide range of wavelengths, from ultraviolet to near-infrared, which is crucial for observing galaxies that are rapidly receding from us due to the expansion of the universe. Hubble's ultraviolet sensitivity, in particular, allows scientists to observe young, hot stars, which are indicators of active star formation and thus of the galaxy's youth. Through this, Hubble has helped trace the star formation rates over cosmic history, revealing how galaxies go through bursts of star birth, followed by quieter periods. One of Hubble's greatest strengths is in its ability to capture spectra, or light patterns, from distant galaxies. Spectroscopy with Hubble has given astronomers insight into the elements present within these early galaxies, showing how the basic building blocks of life, carbon, oxygen, nitrogen, began forming over time. By examining the redshifts in Hubble's spectra, scientists have also been able to accurately measure how fast galaxies are moving away from us, which in turn tells us how far back in time we are looking. Through its many spectroscopic observations, Hubble has pieced together a timeline of galaxy evolution, showing how galaxies became enriched with heavier elements as they merged and reformed in complex ways. Moreover, Hubble's longevity in space has allowed it to document changes over time, which is rare in astronomical observation. With more than 3 decades of data, Hubble has repeatedly observed some galaxies and galaxy clusters, allowing astronomers to identify subtle changes and detect new phenomena. Its long mission has contributed to uncovering complex interactions in galaxy clusters, revealing how galaxies can collide and reshape each other's structure and how supermassive black holes at the centers of galaxies influence their evolution. Hubble's observations are invaluable because they provide a historical record of the universe. By looking at different galaxies at different distances, Hubble essentially looks back in time to trace the universe's history from its earliest stages to its present state. In many ways, it's like watching a movie of cosmic evolution, capturing frames of galaxies at different times. With each observation, it gives astronomers another chapter of the story, piecing together how galaxies like our own Milky Way came to be and how the vast universe became the complex, structured place we see today. Hubble's unique perspective will remain foundational in astronomy for generations, offering a glimpse into the origins of everything we know. The James Webb Space Telescope, JWST, has transformed how we explore and understand galaxies by pushing our observations far deeper into the universe and further back in time than ever before. Unlike the Hubble Space Telescope, which can observe in ultraviolet, visible, and a portion of near-infrared light, JWST is optimized to observe in the infrared. This makes it uniquely powerful for studying distant, early galaxies, as their light, stretched by billions of years of cosmic expansion, has shifted from visible wavelengths into the infrared. Through this expanded infrared capability, JWST has already begun to reveal galaxies from an era only a few 100 million years after the Big Bang, a period that Hubble was unable to fully capture. By observing in the infrared, JWST can also see through the dust that often obscures galaxies, allowing us to glimpse the hidden regions where stars and planets are actively forming. Many of these early galaxies are filled with interstellar dust from supernova explosions and early star formation. This dust blocks visible light, but infrared waves pass through it, exposing intricate details about the galaxy's internal structure. This lets scientists map out dense, previously invisible star-forming regions and study how the very first generations of stars shaped galaxies. Observing these young stars and dust-filled regions helps astronomers understand the conditions under which galaxies grew, evolved, and formed stars, offering insights into how elements and molecules essential to life first emerged. JWST's high sensitivity and resolution allow it to collect more detailed spectra from faint, distant galaxies, giving astronomers new tools to investigate the chemical composition of galaxies in unprecedented detail. By analyzing the faintest spectra, astronomers can detect traces of elements like carbon, oxygen, and nitrogen even in the earliest galaxies, providing clues about how these elements, crucial for life, began to accumulate in the universe. Webb's spectroscopy capabilities go a step beyond Hubble's, letting us see how the chemical makeup of galaxies evolved over time and how stars in the first galaxies forged heavy elements that eventually became the building blocks for planets and life. The JWST has already detected these fingerprints of early chemistry, helping scientists trace the history of matter itself. Another breakthrough with JWST is its ability to image and analyze galaxy clusters, some of the largest structures in the universe, in extreme detail. Its instruments can detect light that has been gravitationally lensed, where massive galaxy clusters bend light from galaxies even farther away. These lensed images allow us to observe galaxies that are so distant they would otherwise be invisible, and they serve as natural magnifying glasses, giving us an incredibly clear look at the structure of these ancient galaxies. By studying such gravitationally lensed galaxies, astronomers can examine how galaxies in different regions of space evolved in response to their environments, and even map the distribution of dark matter, an elusive, invisible substance that influences how galaxies form and cluster. JWST's advanced imaging technology also lets us track galaxy mergers with remarkable clarity. Galaxy collisions and mergers play a critical role in shaping galaxies' evolution, often triggering bursts of star formation and restructuring their shapes. Webb's observations can reveal intricate details of these cosmic collisions, showing how galaxies interact gravitationally and how the massive black holes at their centers impact the merging process. For the first time, we can study the shapes and dynamics of galaxies as they collide, providing key insights into how some galaxies become the large, spiral, or elliptical systems we see today. With the power to see deeper, clearer, and with a broader range of light, JWST is opening a new chapter in our understanding of galaxy formation. Where Hubble provided the initial glimpses, Webb fills in the missing chapters of the universe's early history, taking us back to the earliest galaxies that lit up the cosmos. As it continues its mission, JWST is expected to answer some of astronomy's most profound questions, while revealing new mysteries about how galaxies, our own included, took shape over billions of years. Each image and spectrum from JWST isn't just data. It's a piece of the universe's history, captured with a clarity and depth we could only imagine a decade ago, transforming our understanding of where we come from. Galaxy formation is one of the most fascinating puzzles in astrophysics, and understanding it means diving into questions that touch on the beginnings of structure in the universe, the birth of stars, and the growth of supermassive black holes. We know that galaxies started forming in the early universe, but many aspects of how these vast star cities take shape and evolve remain mysterious. The process appears to hinge on the interaction of dark matter, gas, radiation, and gravity in ways we're only beginning to understand. For instance, we know that dark matter forms the scaffolding that holds galaxies together, but we still don't understand exactly how it shapes the different types of galaxies we see, from spirals to ellipticals. There's also a question about how galaxies stopped forming stars in the first place. Over time, many galaxies ran out of gas or otherwise ceased star formation. Astronomers call these galaxies quenched, but the mechanism by which they shut off their star formation engines isn't clear. Another major unknown involves feedback mechanisms within galaxies themselves. Stars, as they form and eventually die in supernovae, inject energy and matter back into the surrounding gas. Similarly, supermassive black holes, which lurk at the centers of most galaxies, emit jets and radiation that can heat gas and prevent it from cooling and forming new stars. But understanding how these feedback loops work is a massive challenge. Are supernovae or black holes more responsible for heating up the gas and stopping star formation? Does it vary depending on the galaxy's size or other conditions? And do these feedback processes differ for galaxies at different points in cosmic history? The question of merging galaxies also complicates things. Galaxies are constantly pulling on each other, colliding, and merging to form larger systems. These interactions should create distinct features: tails of stars and gas, disruptions, or bursts of star formation. But we still don't have a perfect understanding of what happens during these mergers. Sometimes they seem to spur new star formation, while other times they seem to help quench it, depending on a range of factors, including the gas available in each galaxy. Unraveling these dynamics means examining not only the specific conditions of each galactic pair, but also understanding how such events impact the overall distribution and types of galaxies we see in the universe today. We're also struggling to explain the so-called cosmic web structure of galaxies. When we look at the universe on the largest scales, galaxies are not randomly distributed, but instead lie along vast filaments separated by enormous voids. The reasons for this arrangement aren't fully known, though it's likely tied to dark matter and how it clumped together in the early universe. But why galaxies ended up in these filamentary structures, and how they influence one another within this cosmic web, are questions that continue to challenge researchers. Even the early stages of galaxy formation are shrouded in mystery. Observing very distant, ancient galaxies is like looking back in time, allowing us to see these young galaxies as they existed billions of years ago. Many of them appear to be much more massive or developed than our theories would predict, hinting that something about our understanding of early cosmic evolution is incomplete. Some astronomers propose that we're missing key insights into how quickly galaxies formed in the first place, or that there might be unknown processes at work. Adding to all this are the complexities of metallicity, or the distribution of heavier elements in galaxies. Elements heavier than hydrogen and helium are produced in stars and spread through a galaxy over time, changing how stars form and evolve. But the distribution of these metals across different types of galaxies and over cosmic time is complicated and not fully understood. Metallicity affects everything from the color and brightness of galaxies to the types of planets that might form around stars, so resolving this is crucial to a holistic understanding of galaxies. In every direction, there are challenges to unraveling how galaxies form, grow, and interact. And with each discovery, new questions arise, showing us that galaxy formation is a constantly evolving field, one that brings us closer to understanding our place in the cosmos, even as it keeps its most profound mysteries carefully guarded. Dark matter and dark energy remain two of the most elusive components of the universe, yet their influence on galaxies is undeniable. Dark matter, which makes up a significant portion of the universe's mass, provides the invisible scaffolding around which galaxies form and evolve. It acts like a cosmic glue, holding galaxies together with its gravitational pull despite not interacting with light or any other form of known matter. But the details of how dark matter has shaped galaxies from their earliest stages to their present forms are still largely unknown. We see its effects in the way galaxies rotate. Without dark matter, the stars on the edges of galaxies would be flung into space, as they orbit much faster than the visible mass alone would allow. However, how dark matter interacts with visible matter to create different galaxy shapes, spirals, ellipses, and irregulars, is still unclear. Scientists wonder, for example, if dark matter in early galaxies was clumpy or smoother, and how that affected the development of galactic structure. Dark energy, on the other hand, has a more mysterious role. It was only in the late 20th century that scientists discovered the universe was not just expanding but accelerating in its expansion, an observation attributed to dark energy. This expansion impacts galaxies in complex ways. For instance, as space stretches, galaxies are drawn farther apart, with those further away moving away faster. This expansion affects gravitational interactions between galaxies, making future mergers less common in certain regions of the universe. The current understanding is that dark energy is a force acting on a cosmic scale, pushing galaxies apart, and as time goes on, its influence will only grow stronger. This begs the question: will galaxies eventually drift so far apart that any cosmic structures beyond a single galaxy will become inaccessible or even undetectable from one another? Scientists are also intrigued by the way dark matter halos seem to envelop galaxies. These halos appear as vast regions of invisible mass surrounding galaxies and are crucial to understanding why galaxies don't fall apart as they rotate. But it isn't just their stabilizing effect that intrigues scientists. The The interactions within these halos might help explain why some galaxies grow massive and others stay smaller. Some theories suggest that dark matter may heat surrounding gas or even absorb it, impacting star formation rates within galaxies. The size and density of these halos could help to determine the growth rate of galaxies and whether they tend to form large numbers of stars or fewer ones. This interplay of dark matter and dark energy over billions of years creates a landscape where galaxies evolve in response to forces they can't see. Astrophysicists speculate about how much of this evolution is inevitable and how much is unpredictable, depending on slight fluctuations in dark matter density and the strength of dark energy over time. As galaxies collide or interact, dark matter may reshape the aftermath of these encounters, and dark energy may prevent some galaxies from ever interacting at all. So, while we can make some predictions about future galactic structures, these unknowns leave a huge amount of room for surprises. The lack of direct evidence for either dark matter or dark energy adds to the challenge, as we can't directly observe these forces but only infer their presence from their effects. Researchers are designing sensitive detectors, performing astronomical surveys, and constructing theoretical models to grasp more about their nature. Yet each advancement seems to bring more questions. There's a growing sense that understanding dark matter and dark energy could rewrite our entire understanding of the cosmos, reshaping everything we thought we knew about galaxy formation and the ultimate fate of the universe. In this way, dark matter and dark energy continue to cast a shadow over our knowledge, pulling us forward with the hope that we're one discovery away from finally making sense of these cosmic mysteries. Supermassive black holes, the behemoths lurking at the centers of galaxies, have an outsized impact on galaxy formation and evolution. Though they're often described as hidden or silent, these giants aren't passive players. They actively influence the stars, gas, and dust in their surroundings, shaping the galaxy in ways that scientists are still trying to understand. One of the biggest questions is whether these black holes formed before galaxies, or whether galaxies somehow sparked their creation. Observations of distant, ancient galaxies show that some supermassive black holes appear to have reached enormous sizes surprisingly early in the universe's history, sometimes even before their host galaxies grew significantly. This raises the possibility that black holes could have acted as seeds for galaxy formation, attracting gas and dust that would later form stars and establish the galaxy structure. The impact of supermassive black holes on galaxies goes beyond their gravitational pull. As they consume matter, they release powerful jets and radiation in a process known as feedback. This feedback can create winds strong enough to blow gas out of the galaxy, preventing it from cooling and forming new stars. In this way, supermassive black holes might be responsible for quenching star formation in some galaxies, leaving them largely inactive. Yet, this process is anything but straightforward. Some galaxies, especially in the early universe, show both active black holes and rapid star formation, making it unclear if or when black holes stop star formation entirely. And for some galaxies, instead of halting star formation, the black hole's energy seems to compress the gas around it, triggering star formation. The conditions under which black holes quench or ignite star formation remain an open mystery. The relationship between a galaxy's mass and the size of its central black hole also puzzles astronomers. Observations have shown that the mass of the black hole correlates with the mass of the galaxy's central bulge, suggesting a co-evolutionary relationship. But how could such vastly different structures, one a dense singularity and the other a sprawling collection of stars, grow in lockstep? Some theorists suggest that a feedback loop might link them, where the black hole's activity regulates star formation and vice versa, keeping their masses balanced. But this connection isn't universal, as we see some galaxies with supermassive black holes that appear either too large or too small for their galactic hosts, challenging our theories of coevolution. Supermassive black holes also play a crucial role in galaxy mergers. When two galaxies collide, their central black holes often spiral toward each other, eventually merging as well. The process releases enormous energy, shaking up the galactic environment and potentially triggering new waves of star formation or pushing gas out of the system. These mergers could explain why some galaxies become elliptical or acquire unusual shapes after colliding. Still, it's unclear how common this scenario is or how these mergers might influence the overall growth and evolution of the galaxies involved. As our telescopes and simulations grow more powerful, we keep uncovering layers to the supermassive black hole galaxy connection. Yet with each answer come new questions. The more we study these cosmic giants, the clearer it becomes that they are not just bystanders in galaxy formation. Instead, they are central players in a complex cosmic dance, one that began billions of years ago and continues to shape the universe in ways we are just beginning to glimpse. The role of supermassive black holes in galaxy evolution is likely one of the deepest and most interconnected mysteries in astrophysics, an unsolved puzzle at the heart of our search to understand the universe itself. In the beginning, the universe was remarkably smooth and uniform. A vast sea of energy and particles spread almost perfectly evenly across space. But there were small, almost imperceptible irregularities in this smoothness. Tiny fluctuations in density that had emerged due to quantum effects in the earliest fractions of a second. These fluctuations were incredibly slight, just 1 part in 100,000, yet they carried the seeds of everything we see today. Gravity, the force pulling things together, began working on these tiny differences, pulling slightly denser regions of matter toward each other. It's a bit like a snowball effect, where the smallest accumulations gradually became larger as more matter was drawn in by the force of gravity. These small patches would eventually become the foundations of galaxies, clusters of galaxies, and other cosmic structures. As the universe expanded and cooled, these denser regions began to stand out more clearly, drawing in hydrogen and helium gas. Imagine these regions as cosmic, hot spots, where gravity was quietly but persistently pulling together particles, even though everything else was expanding outward. At first, the matter collected very slowly, but over millions of years, denser pockets began to form. These pockets of gas and dark matter started to collapse in on themselves, and as they did, the pressure and heat increased. Within these dense areas, stars began to ignite, and the first galaxies were born. It's a process that took hundreds of millions of years, but with each step, these regions grew more distinct. Some of the small clouds of gas and stars collided and merged with others, creating larger and more complex structures. Every collision, every gravitational pull, and every burst of star formation was like a small piece of an enormous puzzle, helping to shape the diverse galaxies that populate the universe today. Over time, these galaxies continued to grow, often by merging with other galaxies, forming the massive systems we see now, some with billions or even trillions of stars. These initial fluctuations, seemingly insignificant in the early universe, were magnified over billions of years by gravity, becoming the immense galaxy clusters and cosmic webs that stretch across the universe. The very same quantum ripples that began as tiny variations ended up creating the vast structures that form the framework of the cosmos. And as each galaxy emerged, filled with stars, planets, and eventually the conditions for life, these once small irregularities became part of the story of a universe rich with complexity, shaped by forces set into motion in the earliest moments of time. In the early universe, long before our sun or any familiar stars existed, there was only primordial gas made up almost entirely of hydrogen and helium, remnants from the Big Bang. The conditions were unlike anything we see today. There were no metals, no planets, and no elements heavier than helium. But within these dense gas clouds, the first stars began to take shape. These stars, known as population 3 stars, were massive, hot, and lived intensely short lives compared to later stars. Unlike stars formed today, they didn't have heavier elements to cool them down, so they burned fiercely, consuming their fuel quickly and ending their lives in spectacular supernova explosions. Yet, despite their critical role in seeding the universe with the elements needed for future stars and planets, these early stars remain unobserved. They left no direct traces, only echoes in the chemical makeup of the cosmos. Population 3 stars are like cosmic ancestors that never leave their portraits behind, but their legacy is woven into every atom heavier than helium. When they exploded, they created the first elements beyond hydrogen and helium: carbon, nitrogen, oxygen, and all the other building blocks of life. These elements were scattered into space, enriching the gas clouds that later formed new generations of stars, including population 2 and, eventually, population 1 stars like our Sun. Each generation carried a bit more complexity, with heavier elements that enabled cooler, longer-lived stars to form, and eventually, planets, life, and everything familiar to us. Without these first stars, the universe would have remained a barren place of primordial gas, forever caught in its simplest form. But because population 3 stars burned so brightly, lived so briefly, and ended so explosively, they reshaped the cosmic landscape. They ignited the universe, filling it with light and setting off the process of cosmic evolution that would lead to galaxies, solar systems, and, ultimately, the intricate universe we inhabit. Though we can't see them, the legacy of these stars is imprinted on everything, a hidden lineage of the very first fires that lit up the darkness of the early cosmos. In the quiet reaches of space, galaxies sometimes find themselves drawn to one another, pulled together by the relentless force of gravity. When two massive galaxies meet, it's not a simple merging. It's a collision of cosmic proportions, a dance of stars, gas, and dust caught in an overwhelming gravitational embrace. As these galaxies spiral toward each other, their shapes distort, and stars are flung into new orbits, creating a chaotic, turbulent environment. In this merging process, clouds of gas within each galaxy smash together, compressing and heating as they're forced into tight spaces. This intense compression sets off a dramatic chain reaction. When gas is squeezed to such an extreme, it can suddenly collapse and ignite in massive bursts of star formation. Hundreds or even thousands of new stars are born in this upheaval, flooding the galaxy with fresh light and heat. These starbursts are like fireworks, brief but intense, with vast numbers of stars forming over just a few million years, a fraction of the time galaxies typically spend evolving. The energy from these starbursts is so intense that it can even drive powerful winds, blowing gas out of the galaxies and sometimes halting future star formation by stripping away the very fuel needed to make new stars. In the aftermath of a massive merger, the two galaxies often settle into a single, larger one, transformed by the event. Spiral shapes might flatten or blur, new structures can emerge, and sometimes the newly formed galaxy takes on a different form altogether, becoming an elliptical galaxy or something with entirely new patterns of stars. These mergers are transformative episodes in a galaxy's life, shaking up everything from star formation to its overall shape and future. Far from rare, this cosmic choreography plays out across billions of years, shaping galaxies across the universe and fueling the ongoing cycle of birth, growth, and change in the cosmos. The graceful, sweeping arms of spiral galaxies have an enduring beauty that almost seems to defy physics. As these galaxies rotate, you might expect their arms to wind up and eventually disappear, but they maintain their structure through a subtle, ongoing process. Imagine a crowded city square with people moving in and out. Despite the movement, certain areas are consistently more packed than others. In a similar way, spiral arms are like crowded, traffic zones for stars and gas, areas where the density is naturally higher as everything orbits the galaxy's center. This phenomenon is explained by something called the density wave theory. Spiral arms aren't actually permanent, solid structures. Rather, they're regions where stars and gas clouds are momentarily slowed down and concentrated, creating areas of high density that resemble a visible arm. As gas and stars drift into these dense regions, they're compressed together, which can spark new waves of star formation. Young, hot stars form within the arms and give them their bright, blue glow before burning out quickly, adding to the visual prominence of these regions. The stars within the arms don't stay there permanently. They pass through the arm, just as drivers pass through traffic on a highway. As stars move in and out, the density waves persist, allowing the spiral arms to maintain their form despite the galaxy's constant rotation. In essence, the arms are more like waves on the surface of water. They move around the galaxy with a pattern, not as a rigid structure, but as areas where stars are regularly concentrated, then dispersed. This pattern also means that spiral galaxies can sustain star formation for long periods, as gas clouds repeatedly enter the arms, compress, and form new stars. It's an endless cycle of creation, a natural recycling system that keeps these galaxies dynamic and evolving. These arms are a unique feature that makes spiral galaxies some of the most active, bright, and beautiful places in the universe. Places where stars are born, live their lives, and pass through, leaving behind a shape that, while always shifting, remains familiar. Galaxy clusters are the grand gatherings of the universe, collections of hundreds or even thousands of galaxies bound together by an intricate web of gravity. In these clusters, galaxies don't just sit passively next to one another. They're in constant interaction, their gravitational forces weaving a complex network that affects every galaxy within. Each galaxy contributes to and feels the collective pull of the cluster, a vast gravitational presence that shapes their movements, interactions, and, over time, even their structure. Clusters are not only made up of galaxies, but also contain massive amounts of dark matter, an invisible component that contributes most of the cluster's mass. This dark matter, though unseen, creates an enormous gravitational field that binds galaxies together, even as they try to move apart under their own momentum. Within these clusters, galaxies don't simply orbit. They often interact in ways that change them forever. Some are pulled into close encounters, where tidal forces stretch and distort their shapes, stripping stars, gas, and dust from their edges. Sometimes galaxies even merge, their stars and material colliding and coalescing into new, larger galaxies. This process can trigger bursts of new star formation as gas clouds collide, compress, and ignite, giving the cluster pockets of intense brightness and activity. In other cases, smaller galaxies might be entirely consumed by larger ones, disappearing into them and adding to their mass and structure. These encounters create a kind of cosmic recycling, where galaxies evolve and reshape, merging, consuming, and forming anew over billions of years. Clusters also contain superheated gas, which permeates the space between galaxies and reaches temperatures of millions of degrees. This gas is so hot that it emits X-rays, glowing faintly but steadily in the spaces between galaxies, marking the boundaries of the cluster. When galaxies move through this gas, they experience a phenomenon known as ram pressure stripping, where the pressure from this hot gas removes material from the galaxies, stripping them of the gas needed to form new stars. This stripping process can leave galaxies looking barren, older, and less active over time, slowly draining their ability to create new stars. The entire cluster, with its galaxies, dark matter, and hot gas, forms a gravitational lens that can bend the light of objects behind it. This bending effect allows us to see distant objects that would otherwise be invisible, like looking through a cosmic magnifying glass. These gravitational lenses are natural telescopes, revealing the universe's most distant reaches and giving astronomers a glimpse into the past. Galaxy clusters are a reminder of the interconnected nature of the universe, a gravitational choreography where galaxies, dark matter, and hot gas are bound in a vast cosmic community. Their gravitational interactions create an environment where galaxies are constantly influencing and transforming one another, a vivid display of the forces that shape the universe on its largest scales. The sheer scale and number of galaxies in the observable universe are almost beyond human comprehension. Imagine a night sky that seems infinite and filled with stars. Now, try to picture that each star could represent an entire galaxy, each with billions or even trillions of stars of its own. The observable universe spans about 93 billion light-years across, and within this immense volume, there are likely over 2 trillion galaxies, each one a sprawling collection of stars, planets, gas, dust, and dark matter. Each of these galaxies exists in its own cosmic neighborhood, with stars forming, dying, and evolving within, all while entire galactic structures slowly drift and shift over billions of years. The diversity of galaxies is as staggering as their numbers. There are small, faint dwarf galaxies with only a few million stars, barely visible against the cosmic backdrop. There are massive spiral galaxies like our Milky Way, with their graceful, winding arms that shine with hundreds of billions of stars. Then there are the gigantic elliptical galaxies, some housing trillions of stars, that dominate their regions of space with their vast, oval shapes. And between galaxies lie great stretches of emptiness, called the cosmic voids, creating a kind of vast, three-dimensional web where galaxies cluster along filaments and nodes, shaping the universe's large-scale structure. Looking at the universe on this scale feels like standing at the edge of an ocean where each wave is a galaxy, and the shoreline seems endless. Each galaxy, each cluster, and each filament is part of a cosmic story that stretches back nearly 14 billion years. And within each of these galaxies, stars and planets host potential environments as varied as they are numerous, possibly even nurturing life in forms beyond our imagination. Our own galaxy, with all its richness and diversity, is just one of these countless otherworldly places in a vast tapestry, reminding us that we're part of something much larger than we can truly grasp, an endless realm where the sheer number of galaxies gives just a glimpse of the universe's boundless complexity. The mystery of why galaxies take on different shapes, spiral, elliptical, or irregular, stretches back to some of the earliest stages of the universe and has puzzled astronomers for decades. When looking at galaxies, it's clear that their shapes aren't random. They seem almost sculpted, each type with distinct characteristics and a certain elegance, as if something specific happened to shape each one. Spirals, with their swirling arms, often feature young, bright stars and a lot of gas, suggesting they're actively forming stars. Ellipticals, by contrast, look more like glowing orbs with a smoother, more uniform light, lacking the striking arms and often containing older, dimmer stars. Then there are irregular galaxies, which seem to defy structure entirely, with a chaotic blend of star clusters, gas, and dust scattered in unexpected ways. One theory is that a galaxy's shape might have been determined by the environment it formed in and the specific conditions of its early development. In regions of the universe where galaxies have few close neighbors, they may have grown and evolved mostly undisturbed. Many of these isolated galaxies end up with the spiral shape, with gas and dust gradually condensing and rotating to form the characteristic arms. On the other hand, elliptical galaxies are often found in dense clusters where gravitational interactions are common. It's possible that these interactions, often collisions or near collisions with other galaxies, might have reshaped galaxies that were once spiral, scrambling their structures and reducing their gas supply, which eventually leaves them as older, more settled ellipses with little new star formation. But even this explanation doesn't cover everything. Not every elliptical galaxy resides in a crowded cluster, and some spiral galaxies are found in busier regions where we'd expect interactions to have stripped them of their form. The origins of irregular galaxies are even more elusive. Some irregulars may simply be young galaxies that haven't had enough time to settle into a more organized shape. Others might be disrupted by nearby galactic influences, their gas and stars thrown into disarray by gravity from a larger, neighboring galaxy. Yet not all irregulars have close companions, suggesting that other, less obvious processes are at work, possibly involving factors from the early universe or remnants from the galaxy's initial formation. Some researchers suggest that dark matter, an invisible substance that makes up most of the mass in the universe, might play a role in shaping galaxies. Dark matter's gravity would have guided the formation and clustering of galaxies from the start, influencing how they grew and interacted. While the exact role of dark matter remains speculative, it could help explain why galaxies in different regions behave so differently, sometimes forming smooth ellipses and other times winding into spirals. The truth is, galaxy shapes probably result from a combination of factors: initial conditions, the presence of neighbors, random cosmic events, and perhaps influences that we still don't fully understand. This makes every galaxy a unique record of cosmic history, its shape a kind of fingerprint left by billions of years of events and interactions. Yet the exact forces that determine these forms remain one of astronomy's most intriguing open questions. In the universe, not all galaxies are in a hurry to make new stars. Some are bustling hubs of star formation, while others are like quiet neighborhoods where new stars rarely emerge. This difference in star formation rates between galaxies comes down to factors like available gas, galaxy structure, interactions with other galaxies, and even the influence of massive black holes. Some galaxies, known as starburst galaxies, experience intense episodes of star formation, creating stars at rates 100 times faster than average galaxies. These galaxies have abundant cold gas, which acts as the raw material for stars, and conditions that trigger rapid compression of this gas, sparking bursts of star formation. Often, interactions like galaxy mergers or close encounters stir things up in these galaxies, compressing the gas, heating it, and creating the perfect conditions for rapid star birth. In contrast, some galaxies, especially massive ellipticals, have much lower rates of star formation, or even none at all. These galaxies may have used up or lost most of their cold gas over billions of years, leaving little to fuel new stars. In some cases, supermassive black holes at the centers of these galaxies release powerful jets of energy that heat up surrounding gas, preventing it from cooling and condensing into stars. Without cool gas, star formation slows or stops entirely, leaving these galaxies with older stars and little opportunity for new stars to form. Spiral galaxies like the Milky Way lie somewhere in the middle, with steady star formation rates that maintain the galaxy's structure and create new stars at a moderate pace. In these galaxies, the spiral arms are often the main sites of star formation, where gas and dust are more concentrated and conditions favor star birth. However, even within spirals, star formation rates can vary widely depending on the amount of gas and dust available and whether any interactions with nearby galaxies have sparked new bursts of activity. The environment around a galaxy also plays a role. Galaxies in dense clusters may be stripped of their gas by gravitational forces or by moving through the hot, ionized gas that fills clusters, a process called ram pressure stripping. Without gas, these galaxies lose their ability to form new stars and age into what we call red and dead galaxies, populated by older, redder stars, but with no new ones forming. Meanwhile, galaxies in less dense regions, where gas is still plentiful, can maintain star formation for much longer, creating bright, younger stars that give these galaxies a more vibrant, bluish hue. Understanding the variation in star formation rates is not only a way to measure a galaxy's current state, but also offers insight into its past. Star formation rates reveal the history of galaxy interactions, mergers, and other cosmic events that have shaped each galaxy's evolution. Some galaxies may have once been active star formers, but were stripped of gas or heated by a central black hole's feedback, leaving them in a quiet phase. Others may be just beginning their starburst phase, fueled by a recent encounter that reignited star formation. By studying these differences, astronomers can trace how galaxies evolved, shedding light on the conditions and events that determine when and where new stars will emerge. The cosmic web is the vast, intricate structure of matter that stretches across the universe, linking galaxies together in a massive, interconnected network. At its core, the cosmic web is formed by dark matter, a mysterious, invisible substance that makes up most of the universe's mass. Dark matter doesn't emit or absorb light, but it exerts gravitational forces that shape and anchor galaxies and galaxy clusters, giving the universe its large-scale structure. In the cosmic web, dark matter acts like an unseen scaffold, gathering galaxies into clusters, drawing out long filaments that stretch across space and leaving empty voids between them. This pattern, stretching across billions of light years, resembles a web or a network, where nodes of galaxies sit at the intersections, connected by long, thin strands of dark matter and gas. Understanding this web is like unlocking the skeleton of the universe. Galaxies are not scattered randomly in space. They follow the distribution of dark matter, gathering along the filaments and forming dense clusters where the filaments meet. These intersections are home to some of the universe's largest galaxy clusters, where thousands of galaxies are bound together by gravity. Between these clusters, thin strands of gas and dark matter extend like the highways of space, carrying matter from one cluster to another and connecting different parts of the universe. This network is dynamic, with material slowly flowing along the filaments, fueling star formation and galaxy growth at the nodes. The cosmic web has been mapped out through both observation and complex simulations. Astronomers use telescopes to look at large regions of the sky and detect the distribution of galaxies, then use sophisticated models to simulate the evolution of this structure over billions of years. In these simulations, the early universe begins as a nearly uniform sea of dark matter and gas, but over time, gravity pulls this material together, forming dense nodes and connecting filaments. These simulations reveal how galaxies grow and change along the web and how matter flows along the filaments, shaping the universe into its vast, intricate pattern. Observing the cosmic web directly is incredibly challenging because the individual filaments are faint and hard to detect. However, astronomers have found ways to observe the gas in these filaments by looking at the light of distant quasars, extremely bright objects powered by supermassive black holes in the centers of galaxies. As light from quasars passes through the cosmic web, some wavelengths are absorbed by the gas in the filaments. By studying these absorption lines, astronomers can map out the locations of filaments and even determine the chemical composition of the intergalactic gas. The cosmic web isn't just an arrangement of galaxies. It's the underlying structure of the universe that governs how galaxies form, grow, and evolve. Its influence is so fundamental that the entire cosmic history of galaxy formation is connected to it. As galaxies move and evolve along these dark matter filaments, they pull in gas from their surroundings, fueling star formation and growing supermassive black holes at their centers. The cosmic web essentially provides the scaffolding for galaxy clusters and superclusters, guiding the flow of matter across the universe and creating the framework within which galaxies, stars, and ultimately planets come into being. Understanding this web deepens our sense of the cosmos, revealing a structure that not only holds galaxies together but connects every corner of the universe in a vast, complex network that has shaped everything we see. The phenomenon of quenched galaxies, those that have stopped forming stars, is a mystery that captures a fundamental question about the life cycles of galaxies. Star formation is the heartbeat of a galaxy, giving it its light, shape, and energy. But some galaxies seem to lose this spark, becoming quiet and gradually aging as their stars die off, leaving behind only faded light and dense cores. This raises a profound question. What causes a galaxy to suddenly, or sometimes gradually, lose the ability to make new stars? One theory is that the gas needed for star formation simply runs out or is heated up to the point where it can no longer cool and collapse to form stars. In star-forming galaxies, gas clouds cool and condense under gravity, eventually creating the dense knots that become stars. But in quenched galaxies, the gas may become too hot or be pushed out of the galaxy altogether, disrupting this process. Powerful processes like feedback from supermassive black holes or bursts of intense star formation may contribute to this by heating up the gas or blowing it out of the galaxy's gravitational grip, leaving the galaxy without the essential fuel to create stars. Galaxy mergers also complicate things, as they can either trigger or quench star formation, depending on various factors. In some cases, when galaxies collide, the combined gravitational forces may compress gas and trigger bursts of star formation. But in others, mergers create a chaotic environment where gas is stripped away or heated, halting star formation entirely. This dual role of mergers is puzzling. What determines whether a merger leads to a starburst or quenching? Does it depend on the size of the galaxies involved, or the environment they are in, or something about the timing of the merger? The galaxy's location within a cluster can also influence its star formation. Galaxies at the heart of dense clusters are often quenched, possibly because they've been stripped of gas by their interactions with other galaxies or the cluster's hot, intergalactic medium. This process, known as ram pressure stripping, acts like a cosmic wind, sweeping gas away from the galaxy as it moves through the dense cluster. Yet, not all galaxies and clusters are quenched, suggesting that there may be other factors at play. For example, some galaxies seem to retain their gas despite the pressures of a cluster environment, suggesting that some galaxies have ways of holding on to their star-forming fuel longer than others. Another interesting possibility is that cosmic rays or other energetic particles could play a role in quenching galaxies. Some researchers have proposed that, in certain galaxies, high-energy particles from supernova explosions or black hole jets could keep gas warm enough to prevent it from collapsing into stars. This would mean that the life cycle of massive stars, rather than creating conditions for new stars to form, might contribute to a galaxy's eventual quenching by injecting too much energy into the surrounding gas. The varied ways in which galaxies quench their star formation hint at a complex interplay of environmental factors, internal processes, and chance encounters. Some galaxies might retain the raw material for star formation but are unable to cool it, while others lose their gas entirely due to interactions with other galaxies or a powerful black hole at their core. For each quenched galaxy, there may be a unique history, a series of events and encounters that led it to go quiet. Understanding why some galaxies quench while others continue to form stars could reveal much about the universe's history and give us insights into how galaxies evolve across billions of years. It's a mystery that speaks to the balance between the forces that sustain galaxies and those that push them toward a quieter, lonelier existence. It's almost unfathomable to imagine that only a few 100 million years after the Big Bang, the universe, newly emerged from a dark, shapeless expanse, was already dotted with massive, structured galaxies. Yet, as astronomers peer into the deep past with some of the most powerful telescopes ever built, they're finding these extraordinary structures in the most unexpected places, the dawn of cosmic time. In a universe still raw, still cloaked in the vestiges of its fiery origins, there are galaxies that seem to defy what we understand about formation and growth. These galaxies aren't embryonic clusters slowly drawing together, as one might expect, but fully formed, immense collections of stars and gas with all the hallmarks of systems that should have taken billions of years to assemble. This discovery leaves scientists both fascinated and puzzled, as it challenges nearly everything they assumed about the pace of cosmic evolution. When astronomers look out into space, they're essentially looking back in time. Light from distant galaxies has traveled across billions of light years, only reaching us now. Each photon tells a story from epochs long past, encoding a history that can reveal secrets about how galaxies came to be. With instruments like the James Webb Space Telescope, these glimpses stretch further than ever before, reaching back over 13 billion years. Instead of finding young, chaotic clusters beginning to take shape, astronomers have observed galaxies that already show signs of maturity, structure, density, and sometimes even the early stages of rotation. These galaxies, many formed within the first 500 million years of the universe, shine with a brightness and complexity that is hard to reconcile with the early conditions thought to dominate that period. Galaxies aren't expected to spring into existence fully formed. The process of galaxy formation, as we understand it, should be slow and intricate, driven by the gravitational pull of dark matter halos that draw in gas over eons, creating the conditions for the first stars to form. These stars ignite, die, and enrich the surrounding gas with heavier elements, eventually leading to even more complex stars and structures. To see galaxies that are so developed at such an early time suggests that either the conditions in the early universe were far more conducive to rapid galaxy growth than imagined, or that our models miss a key aspect of how galaxies come together. It's as if these ancient galaxies were rushed into maturity by some force or process we're yet to fully understand. Their existence points to a universe that was able to generate and assemble large-scale structures with a speed that strains the boundaries of current astrophysical theories. Adding to the mystery is the fact that these ancient galaxies, seen with both Hubble and now James Webb, often have a massive, reddish appearance. This red hue comes not only from the incredible distance of these galaxies, but also suggests that they are filled with old stars. Stars that have aged enough to cool and shift toward the red end of the spectrum. Stars themselves take millions to billions of years to evolve and age. So a galaxy filled with mature stars just a few 100 million years after the Big Bang is perplexing. It implies that star formation began extraordinarily quickly in these regions, reaching a fever pitch that brought them to maturity in what should have been cosmic infancy. How did these galaxies compress what we thought was a leisurely, gradual process into such a short time frame? It's a question that lingers as scientists sift through these early images, looking for clues hidden within each pixel. Some theorists suggest that the early universe may have been more densely packed with dark matter, creating powerful gravitational wells that pulled in matter with unmatched intensity, leading to extremely rapid star formation. Others propose that some exotic, high-energy processes fueled the early accumulation of matter, allowing these galaxies to bulk up faster than physics currently predicts. Whatever the case, these fully formed ancient galaxies are more than just anomalies. They could redefine what we understand about the universe's ability to create complex structures. Each of these galaxies, as surprising as it is to find them, is a glimpse of a different story the universe has to tell about its youth. Stories that rewrite the cosmic script on how galaxies should grow and evolve. The more scientists uncover about these ancient, nearly fully formed galaxies, the more they realize how complex and layered the history of the universe must be. Each discovery seems to reveal another question rather than an answer, a reminder that even the best models are ultimately guesses in the face of a cosmos that continually outpaces human comprehension. These distant galaxies, shining from the universe's first moments, might be telling us that our universe, from its very beginning, was shaped by processes that are stranger and more dynamic than any we've yet accounted for. And so, scientists continue to look further back, further into the unknown, hoping to catch the universe in the act of doing what it always does best, surprising us with the depths of its own mysteries. Observing galaxies as they were billions of years ago might seem like science fiction, but it's something we actually do with powerful telescopes. It's as close to time travel as humans can get. Light travels at a fixed speed, about 186,000 miles per second. So when we look at objects very far away, we're seeing them not as they are now, but as they were when that light first left them. For nearby stars, this delay might be just a few years. But for the most distant galaxies, we're looking billions of years back, seeing them as they appeared when the universe was young. In a way, telescopes are like windows that let us peer into the past, revealing snapshots of cosmic history frozen in light. This capability is fundamental to understanding galaxy formation because it lets us watch galaxies in different stages of development. The deeper we look, the further back in time we see, allowing us to trace galaxies back to their earliest, formative stages. By capturing light from these young, ancient galaxies, telescopes like Hubble and the James Webb Space Telescope reveal a universe that was far more chaotic and compact. Early galaxies were smaller, often irregular in shape, and forming stars at an incredibly rapid pace compared to modern galaxies. These images show a universe brimming with young, energetic galaxies colliding, merging, and reshaping each other, their intense star formation lighting up the cosmos. Every new image from these telescopes adds another piece to the puzzle, giving astronomers clues about how galaxies have grown and evolved over billions of years. These observations reveal how galaxies gradually change over time, how smaller protogalaxies merge to form larger ones, and how supermassive black holes, star formation, and galactic collisions all play into a galaxy's development. For instance, by observing galaxies from different time periods, we can see how the rate of star formation has slowed down, how galaxies have settled into stable shapes, and how heavy elements have enriched the cosmos over time. The time travel effect doesn't just help us understand individual galaxies, but also the larger structure of the universe. When we look at the distant universe, we see clusters and filaments of galaxies gradually forming and growing, shaping the cosmic web that spans the universe today. These observations are like a moving picture, with each view representing a single frame in the story of how the large-scale structure of the cosmos came to be. What's remarkable is that all of this information is carried to us on the faint light that took billions of years to reach Earth. Each photon from a distant galaxy has traveled through cosmic history, past massive galaxy clusters, through the gravitational bins of dark matter, and across unimaginable stretches of space and time to finally reach our telescopes. Observing galaxy formation is more than looking back in time. It's like reading chapters of a book that was written in light billions of years ago. Every discovery adds to our understanding of the universe's origin, its evolution, and our own place within it. Population 3 stars were the very first stars to light up the universe, emerging from clouds of hydrogen and helium left over from the Big Bang. These stars were fundamentally different from any that followed. Formed in a universe that was still simple and pristine, these early stars had no trace of heavier elements. No carbon, no oxygen, nothing beyond the hydrogen and helium forged in the first moments of cosmic creation. Without these elements, population 3 stars couldn't cool down like later stars, which allowed them to grow extraordinarily large, often hundreds of times the mass of our sun. They burned fiercely and at extreme temperatures, radiating intense ultraviolet light as they converted hydrogen into helium in their cores. Their enormous size meant they lived fast and died young, their lives lasting only a few million years. A mere blink in cosmic time. When these stars reached the end of their fuel, they couldn't go quietly. The immense pressures in their cores caused them to explode in powerful supernovae, dispersing clouds of new elements into the universe. These explosions were the universe's first fireworks, seeding space with elements heavier than hydrogen and helium for the first time. The remains of these stars, the elements they created in their fiery deaths, spread out to enrich the surrounding gas, setting the stage for the next generations of stars and, eventually, planets, moons, and the building blocks of life. Population 3 stars are still a mystery, as no direct evidence of them has yet been observed. They lived in a time too distant and too dim to be captured by today's telescopes, leaving us only indirect clues about their existence. We know them through their absence, through the absence of heavier elements in the oldest stars we can find, which tells us that there was a time when only hydrogen and helium existed. These stars were the universe's pioneers, creating the very first hints of complexity, the building blocks for everything that followed. Although invisible to us now, population 3 stars are part of our cosmic ancestry, their brief, intense lives marking the first steps in a journey that led to galaxies, solar systems, and ultimately, to us. Spiral galaxies are some of the universe's most elegant structures, with their vast, sweeping arms spiraling out from a dense central core. Their distinctive shape is no accident, but rather the result of millions of years of cosmic forces working together. In the heart of a spiral galaxy lies its central bulge, a densely packed region where older stars cluster close together. This central bulge, glowing brightly, is often orbited by stars and gas clouds that gradually spread outward in a flat, rotating disk. The spiral arms themselves are where the galaxy's magic really comes alive. These arms aren't solid structures, but more like dense traffic jams of stars and gas, caught up in the galaxy's rotation. As material moves through the galaxy, the arms act like a kind of cosmic slow lane, where gas clouds collide and compress. This compression of gas triggers star formation, lighting up the spiral arms with brilliant, young, blue stars. In many ways, the arms are cosmic nurseries, full of new life as young stars shine fiercely before dispersing as they age, only to be replaced by new stars forming in their wake. The formation of a spiral galaxy is a process that takes billions of years. In the early universe, galaxies began as loose, irregular collections of gas, dust, and dark matter. Gradually, under the influence of gravity, they flattened into rotating disks. Over time, as stars moved and gravity shaped their orbits, the spiral arms began to emerge, stabilizing into the beautiful patterns we see today. But the journey isn't static. Spiral galaxies are constantly evolving, influenced by interactions with neighboring galaxies, merging gas clouds, and the ongoing dance of stars within them. This gradual but constant reshaping gives each spiral galaxy its own unique form, creating a cosmic fingerprint that tells the story of billions of years of growth and change, a story still unfolding across the vastness of space. Elliptical galaxies are like ancient cosmic fossils, their evolution driven by a history of mergers, collisions, and the gravitational forces that sculpted their form over billions of years. Unlike the lively, star-forming spirals, elliptical galaxies are largely quiet and stable. Their stars bound together in a spherical or elongated shape with no distinct arms or disk. They started out as smaller galaxies, often spirals or irregulars, that merged over time, drawn together by gravity in a series of dramatic collisions. Each merger disrupted the organized motion of stars, scattering them into all directions, creating a smooth, rounded shape that characterizes elliptical galaxies today. These mergers not only transformed the galaxy's shapes, but also altered their contents. In the intense process of merging, massive waves of gas collided, sparking bursts of star formation. For a time, these young stars shone brilliantly, giving the galaxy a period of vibrant activity. But the furious pace of star formation couldn't last. It quickly used up most of the available gas. Without fresh gas to sustain the creation of new stars, elliptical galaxies became largely inactive. What remained were older stars, which gradually cooled and took on a softer, reddish hue. This aging population gives elliptical galaxies their characteristic golden glow, a light that speaks to their long, quiet existence without the sparkling blue of newly formed stars. Central supermassive black holes also played a role in the evolution of elliptical galaxies. During galaxy mergers, black holes from each galaxy often merged as well, growing in size and power. These supermassive black holes could emit powerful jets and winds that swept away any remaining gas, effectively shutting down any potential for further star formation. This created an environment where the galaxy could no longer renew itself, reinforcing its quiet, stable nature. Elliptical galaxies may not have the vibrant star-forming regions of spirals, but their history is written in their structure and composition. They're massive and densely packed, with stars that move in all directions, almost like a swarm. Their smooth, featureless appearance is a testament to countless cosmic interactions, each merger and collision leaving a mark on the galaxy's evolution. Today, they sit as some of the universe's oldest, most settled residents, their days of growth and change long behind them. Yet, they offer a glimpse into the past, standing as monuments to a time when galaxies were pulled together, reshaped, and changed forever by the relentless forces of gravity. The universe is not just a random scatter of galaxies. It's an intricate web, a cosmic structure that links galaxies across vast distances, weaving them into something far larger than the sum of their parts. This cosmic web is a network of dark matter and gas that forms a framework, guiding galaxies along invisible filaments that stretch like tendrils across the cosmos. Imagine a spider's web on an immense scale, where the threads connect galaxy clusters, while voids, vast empty spaces, lie between them. These filaments are not only pathways but also the bones of the universe, giving it structure and shape over billions of years. Dark matter, which neither emits nor absorbs light, is central to this web, creating a scaffolding that ordinary matter clings to, forming stars, galaxies, and clusters along these dark pathways. The cosmic web formed shortly after the Big Bang, when slight density variations in the early universe caused matter to clump together under gravity. Over time, these clumps grew, drawing in more and more material and slowly forming a connected network. Gas followed the dark matter, flowing along these filaments and gathering in regions where the filaments intersect. These intersections became the birthplaces of galaxy clusters, vast collections of galaxies tightly bound together. Galaxies move along these filaments, drawn toward denser regions, in a continual migration that brings them together to form larger structures and shapes their distribution across the universe. Even though galaxies within the web can be separated by millions of light-years, they are still subtly linked by this framework, as gravity pulls them toward each other along the web's filaments. When galaxies fall along these strands toward larger clusters, they can be influenced by tidal forces, compressed and stretched as they move, and even drawn into the dense hubs of galaxy clusters. These interactions are gentle over cosmic timescales, but profound in their impact, shaping galaxies and drawing them closer together. The web also acts as a cosmic highway for gas, funneling it into galaxies and clusters where it can fuel star formation, creating bursts of new stars in regions of higher density. The structure of the cosmic web gives us a way to visualize the universe not as a series of isolated objects, but as an interconnected network, an organic, ever-evolving entity. The galaxies, clusters, and voids are not static. They evolve over billions of years as matter flows through the web, building and reshaping its structure. Observing this cosmic web allows us to understand the invisible architecture of the universe, a network that holds galaxies in a delicate balance, subtly guiding their movements and influencing their fates. Through this web, we see the universe not just as a space filled with stars and galaxies, but as a grand design, a vast and interconnected network where each galaxy is a small part of a larger whole, tied together across space and time. Starburst galaxies are places of extraordinary energy and creation, where stars are born at a rate far exceeding the usual pace found in most galaxies. This intense star formation isn't the galaxy's typical rhythm. It's more like a brilliant, consuming fever sparked by unusual circumstances. Often, this burst of activity is triggered when two galaxies interact or collide, stirring up vast clouds of gas and dust. These collisions create shock waves and gravitational waves that ripple through the galaxy, compressing gas and dust into dense pockets that ignite into new stars. The environment becomes a cosmic nursery where stars form rapidly, many of them massive and bright but destined to burn out quickly. This furious star-forming phase changes the galaxy's appearance and character. Bright blue and white clusters appear as these young, massive stars shine intensely, overpowering the older, dimmer stars around them. The energy output is immense, with intense radiation and stellar winds pouring out from the newborn stars. Massive stars, due to their short lives, die as supernovae soon after they're formed, injecting even more energy back into the surrounding gas and dust. This cycle of creation and destruction feeds the starburst, as each supernova explosion shocks the surrounding material, potentially triggering further star formation in nearby regions. But this period of intense star formation can't last forever. Starbursts are fleeting on cosmic timescales, often lasting only a few million to a few 100 million years. The furious star-making consumes the galaxy's supply of gas, the very fuel needed for continued star formation. Eventually, as the available gas is depleted and the supernovae blow out remaining gas, the galaxy settles back down, leaving behind a mix of older stars and remnants of the younger ones. In many ways, a starburst galaxy is both at its brightest and most vulnerable. The stars it creates in such a short time span ultimately shape the galaxy's future, even as the starburst exhausts the resources needed to continue at that pace. It's a brilliant but unsustainable phase, a cosmic flash of intense life and energy, marking a period of transformation that will determine the galaxy's path for billions of years to come. The galactic halo surrounds the visible parts of galaxies like a ghostly shell, containing some of the most ancient stars and mysterious material in the universe. Unlike the bright spiral arms or dense central bulge of a galaxy, the halo is faint and hard to see, stretching far beyond the main disk and enveloping the galaxy in an almost invisible cloud. But what makes the halo intriguing is its composition. It's not just made up of stars, but also an enigmatic mix of gas and dark matter. The stars within the halo are old, some among the first stars to have formed in the galaxy. They're typically arranged in spherical clusters called globular clusters, orbiting the galaxy in paths that reveal just how ancient and unstructured this region really is. These stars are low in heavy elements, a clue to their origin in the very early universe, before many generations of stars had produced the heavier elements now common in younger stars. The halo's gas is another mystery. Unlike the cool, dense gas that fills a galaxy's disk, the halo's gas is extremely hot, sometimes millions of degrees, yet also incredibly diffuse, spread out over vast distances. This hot gas emits faint X-rays, revealing its presence, but astronomers still don't fully understand how it got there or why it's so hot. It's possible that it's been heated by ancient supernova explosions or interactions with the intergalactic medium, but its exact origins remain unclear. This gas might even be a relic from the galaxy's formation, left over from the early stages of the universe, or it could have come from interactions with other galaxies or from the galaxy itself, as supernova-driven winds expelled material into the halo over billions of years. But perhaps the most enigmatic part of the halo is the presence of dark matter. Dark matter is a form of matter that doesn't interact with light, making it invisible, yet it has mass and exerts gravitational pull. Observations show that the mass of visible stars, gas, and dust in galaxies doesn't account for the strong gravitational forces holding them together. Instead, scientists believe that the halo is where most of a galaxy's dark matter is concentrated, creating a massive but unseen presence around the galaxy. This dark matter skeleton could be what shapes and stabilizes galaxies, providing the gravitational foundation for their formation and evolution. Despite being invisible, the dark matter in the halo holds galaxies together, exerting a gravitational influence that keeps them from drifting apart even as they spin. The galactic halo is therefore a layered mystery, a mixture of ancient stars, blazing hot gas, and invisible dark matter, each part revealing a fragment of the galaxy's past. It represents not only a record of the galaxy's formation, but also hints at forces we have yet to fully understand. The halo's stars point to an early, chaotic time. The hot gas raises questions about galaxy evolution and the dark matter, its true nature still unknown. Challenges our fundamental understanding of matter itself. Together, they make the halo a strange, silent witness to a galaxy's entire history, floating just beyond our view yet woven into the very structure of the cosmos. The James Webb Space Telescope, JWST, is giving astronomers a chance to look farther back in time than ever before, into an era when the first galaxies were just starting to form. Its powerful infrared capabilities allow it to peer through dust clouds and detect faint light from galaxies formed over 13 billion years ago, mere hundreds of millions of years after the Big Bang. This light has been traveling through space for so long that it has shifted into the infrared range, stretched by the expansion of the universe. A phenomenon known as redshift. JWST's infrared sensors are perfectly tuned to capture these distant signals, making it possible to study some of the universe's earliest galaxies in unprecedented detail. With the JWST, scientists are not just identifying early galaxies, but also learning about their structure, size, and composition, shedding light on how they formed and evolved. Early galaxies were likely quite different from the galaxies we see today. They were smaller, more chaotic, and had irregular shapes, with stars forming rapidly from clouds of gas and dense clusters. JWST's observations have confirmed that these galaxies were indeed far more compact and dynamic, with star formation rates that sometimes rival or exceed those of today's galaxies, despite their smaller size. By studying them, researchers can piece together how galaxies grew and transformed over cosmic time, merging with others and evolving from irregular shapes to the more stable spirals and ellipticals that now fill the universe. One key area of interest is understanding how these early galaxies affected their surroundings, particularly during a period known as the epoch of reionization. This was a time when intense radiation from young stars in these early galaxies reionized the surrounding hydrogen gas, turning the universe from an opaque fog into a transparent cosmos. JWST is helping astronomers understand how much these galaxies contributed to this crucial phase. By studying their light, scientists can estimate the number of massive, young stars they contained and gauge their role in reionizing the early universe. The telescope's observations are also helping to uncover the presence of heavier elements, like carbon and oxygen, in these young galaxies. Elements heavier than hydrogen and helium were produced through nuclear fusion in the hearts of stars, meaning that the presence of these elements in early galaxies indicates that they had already experienced one or more generations of stars. JWST is allowing scientists to trace this cosmic metallurgy as it unfolds, revealing how quickly stars formed, lived, and died in the young universe, and how their remnants enriched the interstellar medium, setting the stage for the complex chemistry that would eventually lead to planets and, potentially, life. JWST's search for early galaxies is more than just an investigation into the past. It's reshaping our understanding of the universe's entire evolutionary history. Each discovery reveals something about the origins and development of galaxies, challenging previous theories and inviting new questions about how the first stars ignited, how galaxies clustered together, and how structures as vast as galaxy clusters began to form. The data is so rich and detailed that it's likely to keep scientists busy for years, piecing together the story of the universe's early days. By revealing glimpses of galaxies in their infancy, JWST is giving us a front-row view of the universe's own origins, allowing us to watch the process that would eventually lead to the cosmic landscape we live in today. The Milky Way has undergone billions of years of change and growth, evolving from a chaotic, early galaxy into the magnificent spiral we see today. Its history is complex and filled with periods of star formation, collisions with smaller galaxies, and the gradual gathering of material. Like many galaxies, the Milky Way started as a collection of gas, dust, and dark matter. Over time, gravity drew this material together, forming clumps that merged, grew, and eventually settled into a more structured form. At its core, the Milky Way's dense center began to host increasingly complex interactions, sparking the birth of stars and laying down the foundation for the galaxy we know. One of the key drivers of the Milky Way's growth has been its interactions with other galaxies. Smaller galaxies have collided with and been absorbed by the Milky Way, adding new stars, gas, and dark matter to its mass. These mergers have left behind subtle streams of stars, known as stellar streams, that still orbit our galaxy as remnants of those ancient collisions. These mergers have helped the Milky Way build up its spiral structure, which now spans over 100,000 light-years, and have likely played a role in creating its distinctive spiral arms. The Milky Way's halo, a vast, faint region of stars and dark matter surrounding the main galaxy, also contains remnants from these past collisions, preserving a record of the Milky Way's mergers over billions of years. Our galaxy continues to evolve, shaped by both internal and external forces. Within the Milky Way, new stars are still forming, especially in its spiral arms where gas and dust are concentrated. Massive stars live short, intense lives, ending in supernova explosions that enrich the surrounding gas with heavier elements and create shock waves that trigger more star formation. This cycle of birth and death keeps the galaxy alive with activity and has gradually enriched it with the building blocks of planets and life. The supermassive black hole at the center of the Milky Way, Sagittarius A*, also influences the galaxy's evolution, though it's relatively quiet compared to the active black holes found in some other galaxies. Every so often, however, material falls into this black hole, releasing bursts of energy that can affect star formation in the surrounding region. Looking to the future, the Milky Way's evolution is far from over. In around 4 billion years, it is expected to collide with the Andromeda Galaxy, the Milky Way's nearest large neighbor. This collision will be a slow, drawn-out process lasting billions of years, during which the two galaxies will spiral toward each other, merge, and eventually form a single, massive elliptical galaxy. When Andromeda and the Milky Way collide, the gravitational forces will disrupt the galaxy's structures, triggering waves of star formation as gas clouds compress and merge. While individual stars are unlikely to collide due to the vast distances between them, the collision will dramatically reshape both galaxies. The spiral arms will disappear, replaced by a more rounded, elliptical shape, and the central black holes of both galaxies will likely merge, forming a single, even more massive black hole. This future collision is a natural part of the life cycle of galaxies, particularly those like the Milky Way that reside in galaxy clusters. While this event will signal the end of the Milky Way as we know it, it will also mark the beginning of a new galactic form, a massive, combined galaxy with a history spanning from the Big Bang to the far future. Though this change is billions of years away, understanding it gives us insight into the life cycle of galaxies, helping us appreciate the Milky Way's journey and what may eventually become of our galactic home. In a sense, the Milky Way is not static. It's on a trajectory, part of a grand cosmic dance, shaped by countless interactions and bound to a future that will ultimately merge it with its galactic neighbors, continuing the cycle of growth and transformation that has driven the universe since its beginning. Rogue galaxies, those wandering alone in the vast stretches of intergalactic space, are some of the universe's most intriguing loners. While most galaxies are bound within clusters, groups, or cosmic filaments, tethered together by gravity and often influencing one another, rogue galaxies have drifted free from these ties. Picture them as celestial drifters, untethered and isolated, moving through the emptiness between clusters, far from the crowded galactic neighborhoods where star formation, mergers, and other interactions keep things lively. These galaxies exist in isolation, traveling through some of the darkest, most desolate reaches of space, and astronomers are still piecing together how they ended up there. One theory is that some rogue galaxies were once part of larger galactic groups or clusters, but were ejected after powerful gravitational interactions. In dense galaxy clusters, galaxies are constantly interacting, sometimes even colliding. When multiple galaxies move too close, complex gravitational forces can accelerate one of them to speeds high enough to break away, flinging it out into intergalactic space. This slingshot effect can send galaxies on long journeys, forever severing them from their original groups. For these galaxies, this ejection could be a one-way ticket to a lonely existence, as there's very little chance they'll encounter other galaxies once they're cast out into the cosmic void. Some rogue galaxies might have been born in isolation, forming in regions of space where there simply wasn't enough gravitational pull from nearby clusters to bind them. These galaxies are often smaller and less massive than those in clusters because they formed without the gravitational support and material richness that cluster environments provide. In such isolated regions, the gas density is low, so the rate of star formation is often slower, and their evolution can be very different. These galaxies exist in a kind of cosmic solitude, evolving at their own pace, untouched by the competitive energy and frequent interactions that shape galaxies within clusters. Life as a rogue galaxy presents unique challenges and advantages. Isolated galaxies may avoid the disruptions of gravitational interactions and mergers, which means they could maintain a more stable structure over billions of years. However, they're often stripped of opportunities for fresh star formation. Without nearby galaxies to pull in new material, they risk running out of the gas needed to form new stars, potentially aging more quickly and reddening as their youngest, hottest stars burn out without replacements. For astronomers, this solitude presents a rare glimpse into galactic evolution untainted by external forces. Studying rogue galaxies allows scientists to see what happens when galaxies are left to develop in a kind of cosmic vacuum, untouched by the complex dynamics that influence more social galaxies. Another mystery of rogue galaxies is how they survive in such isolated conditions. Without the regular inflow of gas or opportunities to merge with other galaxies, it's unclear how they sustain any new star formation over time. Some studies suggest that these galaxies might occasionally pass through denser cosmic filaments or clouds, allowing them to refuel by absorbing stray gas in the intergalactic medium. Others may contain unusually large reserves of gas from their formation, a resource that helps them slowly produce new stars over longer timescales than galaxies in clusters. The study of rogue galaxies touches on fundamental questions about cosmic evolution. Are they the last remnants of galaxies cast out from clusters, or are they more ancient, having formed alone in an empty universe long ago? Understanding these wanderers provides insight into the forces that can isolate a galaxy from its peers and into the surprising ways galaxies can survive in conditions far removed from the familiar influences of clusters and groups. Rogue galaxies are, in a way, cosmic time capsules, unusually quiet and isolated, holding clues to how galaxies live and die in the empty spaces between the stars. They stand as a reminder of the unpredictable forces that shape the cosmos, of galaxies that defy the norm, carving out their own paths through an otherwise dark and silent intergalactic wilderness. When we look at the night sky and see stars sprinkled across the vastness, it's easy to imagine them as independent beacons, each shining alone. But stars aren't isolated. They're shaped, guided, and sometimes even destroyed by the galaxies they call home. A galaxy's gravitational field dictates where stars are born, how they move, and ultimately, how they die. And when we trace the life of a star back to its earliest days, its fate is intertwined with the structure and dynamics of its galaxy. as though the galaxy itself has laid out a path, subtly nudging the star through phases of life that might appear individual but are tied to the larger cosmic framework. In the dense, spiraling arms of galaxies like the Milky Way, gas and dust swirl in tight formations, continuously compressed and shaped by the galaxy's rotation and gravitational pull. These arms are stellar nurseries, places where gas clouds are packed together, triggering the formation of new stars. These aren't random birthplaces but orchestrated regions where the galaxy, with its massive gravitational forces, determines the density and flow of material that allows new stars to emerge. Every star born here inherits the movement, velocity, and orbit imparted by the galaxy's structure. As the young star ignites and begins its life, it does so within a system that dictates where it can travel, who its neighbors will be, and even what kinds of encounters it might have. It's as if the galaxy molds the destiny of its stars, giving them paths to follow from their very first moments. But galaxies aren't static entities. They evolve over billions of years, undergoing collisions and merging with neighboring galaxies. These titanic interactions send shockwaves through star systems, altering orbits and sometimes even igniting bursts of star formation. A solar system within such a galaxy experiences these changes on a cosmic scale. Imagine a peaceful star and its planets suddenly drawn closer to a neighboring star system as the galaxy reshapes itself. The changes may be imperceptible on human timescales, but over eons, entire solar systems can shift, sometimes destabilized as they are swept into new galactic regions, experiencing gravitational influences that can disrupt planets or even pull them away from their parent stars. The galaxy's influence extends even to the way stars live and die. Massive stars, born in regions dense with gas, often exhaust their fuel in just a few million years, ending their lives in violent supernovae. These explosions aren't just the death of a star, but a release of energy that can trigger the birth of new stars nearby, seeding the galaxy with heavier elements. These elements become the building blocks for new stars and planets, enriching the galaxy and creating a cycle of life and death that ensures no two generations of stars are quite the same. A solar system like ours, with a planet as complex as Earth, wouldn't exist without this recycling of material. The galaxy's structure, with its dense star-forming regions and expansive arms, makes possible this continual renewal, dictating which areas have the raw materials for future solar systems to emerge. In regions where star formation has slowed, such as the galaxy's outskirts, stars often have quieter, more solitary lives, and their planetary systems, if they form, tend to remain stable. These stars experience less gravitational interference and are less likely to encounter other systems. For a planet orbiting a star in such a quiet region, the galaxy's influence feels almost distant, a faint gravitational reminder rather than an active presence. But even here, the galaxy's overarching mass holds them in place, anchoring them to a path that, while calm, is part of the galaxy's grand rotation. The end of a star's life also ties it back to the galaxy in unexpected ways. As stars die, especially in the galaxy's dense core, they can collapse into neutron stars or black holes, remnants that continue to exert gravitational influence on their surroundings. In the center of galaxies like the Milky Way, supermassive black holes dominate, pulling stars in closer, shaping the movement of countless nearby systems. These black holes feed off surrounding material, and their gravitational might can bend entire star systems around them, forming complex orbits and sometimes flinging stars out of the galaxy altogether. For stars in these central regions, their fates are inextricably bound to these cosmic giants, each motion influenced by forces that pull them closer or sometimes propel them far into the intergalactic void. The galaxy, in all its sprawling complexity, is like a cosmic choreographer, setting each star on a unique journey yet anchoring them all to a shared rhythm. Each star's light, every planet's orbit, and every comet's path speaks to the galaxy's pull, its ability to shape lives and destinies across unimaginable distances and timescales. For us, living on a planet bound to a modest star on a galactic arm, the galaxy's influence is ever-present. A gentle but unyielding force that has directed every stage of our solar system's history and will continue to do so as the Milky Way evolves, carrying us along in its vast, intricate dance. And that brings us to the end of this cosmic journey through the formation of galaxies. From the early chaos of the Big Bang to the shaping power of dark matter, the brilliance of the first stars, and the spectacular collisions that molded galaxies into what we see today. It's a story that spans billions of years, yet still holds so many mysteries. Thank you for joining Quiet Universe on this exploration. We hope we've sparked your curiosity about our galaxy and the vast cosmic neighborhood beyond. If you enjoyed this journey through the stars and want to dive into more of the universe's secrets, don't forget to give us a like. And if you're ready to travel even deeper into the wonders of space, make sure to subscribe. Until next time, keep looking up and keep wondering.